Hold onto your hats, folks, because what I'm about to share will blow your mind. The sun just pulled off something that has scientists scratching their heads and conspiracy theorists buzzing with excitement. We're talking about a massive hole, tearing across the sun's surface, spewing a river of plasma directly at Earth. And get this, at that exact moment, Comet 3 I Atlas, our second ever confirmed interstellar visitor, completely vanished from every telescope. To top it all off, Mother Earth decided to join the party with some serious shaking. The million-dollar question on everyone's lips: what in the universe just happened? Was this cosmic visitor destroyed or transformed? And if it does re-emerge, what might it look like? While one comet plays hide-and-seek, another is stealing the spotlight. Say hello to Comet Lemon, an ancient icy relic that's been cruising through space since before humans even built their first cities. This cosmic snowball is racing across our skies right now, and I'm here to tell you why the next 2 weeks are absolutely critical for skywatchers. Meanwhile, over in China, physicists have achieved something straight out of a sci-fi blockbuster, an unhackable communication network that's basically the ultimate tattletale. And don't even think about blinking, because before we wrap up, I'll reveal some cosmic dates you absolutely cannot miss, including one that nobody's talking about yet, but should be. If these mysteries have you on the edge of your seat like they do me, don't just sit there, take action. Hit that like button, smash subscribe, and stay locked in as these stories unfold in real time. Drop a comment with where you're watching from, what time it is there, and tell me straight up, do you believe we're getting the whole truth about these world-shaking discoveries? And hey, if you want to help this community grow, share this video on X, Facebook, Reddit, or even your group chats. Every share, every comment, every click fuels our investigation. You're the reason we can keep chasing these mind-bending stories. So thank you for standing with us in this cosmic search. Let's dive into part 1, the disappearance. October 2025 arrived with a cosmic alarm bell that most people never even heard. Scientists monitoring our star watched with growing unease as a massive transequatorial coronal hole ripped open across the solar surface. Picture this: a gash in the sun's magnetic field that looked like a wound bleeding invisible energy into space. This wasn't your run-of-the-mill solar activity that produces pretty auroras and maybe messes with a few satellite signals. Nope, this hole was enormous, spanning regions of both the northern and southern solar hemispheres simultaneously, a configuration that happens about as often as a blue moon. And with consequences we're just beginning to wrap our heads around. The solar wind pouring through this tear in the sun's magnetic armor hit speeds of 700 kilometers per second. To put that in perspective, imagine a hurricane where every particle of air is moving at nearly 1.5 million miles per hour. This stream of charged particles, protons and electrons stripped from their atoms, came screaming toward Earth like a cosmic fire hose aimed directly at our planet's magnetic field. The alignment was perfect, almost suspiciously so. The magnetic polarity of the solar wind matched Earth's field orientation in precisely the configuration needed for maximum coupling, the strongest possible transfer of energy from the sun's breath into our planetary magnetosphere. Geophysicists scrambled to predict the impacts. Power grid operators received warnings. Satellite controllers prepared for possible malfunctions. Aurora chasers packed their cameras and headed north, knowing this kind of solar assault would paint the sky in colors that defy description. But something else happened at that exact moment. Something that would turn this solar event from a routine space weather episode into a genuine cosmic mystery. Comet 3 I Atlas, the second confirmed interstellar visitor ever detected in our solar system, disappeared behind the sun. One moment, it was there, a faint smudge of light moving on an orbit that originated in another star system, carrying ice and rock that formed in alien clouds around a sun we'll never see. The next moment, it vanished into the solar glare, swallowed by the overwhelming brightness of our star, rendered invisible to every telescope on Earth and in space. The timing was impossible to ignore. Earth's magnetic field getting hammered by the fastest solar wind in months, and simultaneously our only accessible interstellar messenger going dark behind the very source of that assault. Scientists are careful people, trained to avoid jumping. Two conclusions, conditioned to repeat the mantra that correlation does not equal causation. They measured their words carefully when reporters asked if these events could be connected. Then the earthquakes started. Multiple magnitude 7 earthquakes struck different regions of Earth within hours of the solar wind's arrival. Recorded the violent shaking, the sudden release of tectonic energy that had been building for years, perhaps decades, in the stressed rock beneath our feet. The tremors weren't unexpected in a statistical sense. Earth experiences roughly 15 magnitude, 7 earthquakes every year on average, but having several occur in close temporal proximity to a major solar event and the disappearance of an interstellar comet triggered something in the human pattern recognition system, that ancient part of our brains that searches for connections, that demands meaning from coincidence. Could the sun's magnetic assault on Earth have somehow triggered seismic activity? The mainstream scientific consensus says no. That's not how earthquake physics works. Tectonic plates don't care about magnetic fields or solar wind. They grind and slip according to the laws of rock mechanics and accumulated strain energy. But there are other voices, researchers working at the fringes of geophysics who point to statistical anomalies in earthquake timing during solar maxima, who suggest mechanisms involving ionospheric coupling or subtle changes in Earth's rotation rate. These ideas haven't gained traction in peer-reviewed literature, but they circulate in conference hallways and online forums, whispered possibilities that the mainstream hasn't yet disproven to everyone's satisfaction. The comet, though, that's where the real mystery lives. 3 I Atlas earned its designation as the third confirmed interstellar object detected passing through our solar system. The first was 1 I Oumuamua in 2017. That bizarre, elongated thing that tumbled through the inner solar system and exhibited acceleration that couldn't be fully explained by normal comet outgassing. The second was 2 I Borisov in 2019, which looked and behaved more like the comets we're familiar with, a reassuring ball of ice and dust that followed predictable physics. 3 I Atlas was discovered in 2025, tracked as it fell toward the sun on a hyperbolic orbit, moving too fast to be bound by our star's gravity. Clearly a visitor just passing through on its way. back to interstellar space. These objects are incredibly precious to science. They're the only samples we have of material from other stellar systems, at least until we develop the technology to send probes to nearby stars and return with physical specimens, something that won't happen in any of our lifetimes. Every photon of the light we collect from an interstellar comet carries information about chemistry, about the composition of protoplanetary disks around other suns, about whether the processes that formed our solar system are universal or unique. When 3I Atlas disappeared behind the sun, we lost our ability to gather that data, at least temporarily. The question that haunts astronomers now is simpler and more disturbing than any of the speculation about solar, wind, or earthquakes. When 3I Atlas emerges from behind the sun, if it emerges at all, will we recognize what comes out? Did the sun just eat our interstellar visitor? Could the intense heat and radiation and magnetic turbulence near our star have reshaped it, broken it, parred, vaporized it entirely? We're about to find out, and the answer might append everything we think we know about these alien wanderers. Let's rewind the clock and piece together how we stumbled upon this cosmic mystery. The story of 3I Atlas begins like most comet discoveries do, with patience. With automated telescopes scanning the sky night after night, looking for anything that moves against the background stars, the Atlas Survey, short for Asteroid Terrestrial Impact LAS Alert System, consists of 4 robotic telescopes distributed around the globe, designed primarily to spot asteroids that might pose a collision threat to Earth. But these telescopes don't discriminate. They capture anything that moves, including comets. And in the early months of 2025, they captured something extraordinary. The object first appeared as a faint streak in images from the Hoying stations. Follow-up observations from other facilities confirmed it was moving, and moving fast. Trajectory calculations revealed the telltale signature of a hyperbolic orbit, an eccentricity greater than 1, meaning this thing wasn't bound to our sun. It came from somewhere else, and after its close approach to our star, it would leave, headed back into the cosmic ocean between stars. The orbital energy was wrong for a solar system native. This was interstellar, no doubt about it. The astronomy community mobilized faster than you can say Eureka. Telescope time, always scarcer than water in the desert and competed for months in advance, was suddenly made available. Spectroscopy, the analysis of the light reflected or emitted by the comet, became the top priority. What was this thing made of? Did it contain the same mix of water, ice, carbon dioxide ice, and organic molecules that characterize comets born in our solar system? Or would its composition reveal alien chemistry, ratios of elements that pointed to formation conditions around a different type of star? Early data suggested something puzzling. The brightness of 3I Atlas didn't behave quite like astronomers expected. Comets typically brighten as they approach the sun, following a predictable curve related to the increasing sublimation of ice. As solar heating intensifies, water ice starts subliming, turning directly from solid to gas when sunlight warms the surface to around 200 Kelvin. Other volatiles, like carbon monoxide and carbon dioxide, sublimate at even lower temperatures, creating activity at much greater distances from the sun. But the brightness curve of 3I Atlas showed flattening periods where the comet didn't brighten as much as models predicted, followed by sudden jumps in luminosity that suggested discrete outbursts of dust or gas. The comet, the fuzzy cloud of gas and dust surrounding the nucleus, appeared unusually faint in some observations. Dust production seemed lower than expected for a comet of its size. Some researchers speculated the nucleus might have an unusually high density, more rock than ice, which would explain the weak activity. Others suggested the opposite. The nucleus was extremely porous, almost like a rubble pile held together by weak gravity, and that this structure was causing the ice to sublimate in unpredictable bursts rather than steadily. Then there were the non-gravitational forces. Comets don't follow pure Keplerian orbits, determined solely by the sun's gravity. When ice sublimates from the nucleus, it creates jets of gas that act like tiny rocket engines, pushing the comet slightly off its predicted path. These accelerations are small but measurable, and they introduce uncertainty into predictions of exactly where a comet will be at any given time. For 3I Atlas, these perturbations were particularly difficult to model. The orbit calculations kept getting refined, the error bars kept shifting, and astronomers grew increasingly uncertain about precisely when and where the comet would reappear from behind the sun. Some observations hinted at possible fragmentation. Before the disappearance, comet nuclei are fragile things, weakly bound collections of ice and rock that can split apart under thermal stress or tidal forces. When a comet fragments, it often creates a train of smaller pieces following similar orbits, sometimes visible as multiple condensations in the coma. Imaging of 3I Atlas showed possible asymmetries, elongations that might indicate the nucleus was beginning to come apart. If the comet was already fragmenting before it disappeared, the question becomes even more pressing. What will emerge from the solar glare? Might not be a single object, but a stream of debris, or perhaps nothing at all if the fragments became too small to detect. The comparison to previous interstellar visitors was inevitable. 1I Oumuamua, that first detected interstellar object, was never confirmed to be a comet. It showed no visible coma, no dust tail, nothing that would definitively identify it as an icy body. Yet, it accelerated away from the sun in a manner that couldn't be explained by gravitational forces alone. The most likely explanation remained comet outgassing, but of a volatile more exotic than water, possibly carbon monoxide or molecular nitrogen substances that would sublimate without producing visible dust. The alternative explanations, from light sails to alien probes, captured public imagination but found little support among scientists who deal in evidence rather than speculation. 2I Borisov behaved more like a familiar comet with a proper coma, and tail and brightness variations that matched standard comet models reasonably well. Its spectrum revealed water vapor and carbon monoxide, chemistry similar to what we see in solar system comets. This was reassuring, in a way suggested that planetary formation around other stars follows similar rules, produces similar objects. But Borisov also showed signs of fragmentation near perihelion, its closest approach to the Sun. Images captured what appeared to be a small chunk breaking away from the main nucleus, a reminder that these interstellar travelers don't always survive their passage through the inner solar system intact. Now 3I Atlas was following a similar path, diving toward the Sun, and we'd lost sight of it at the worst possible moment. The geometry of solar conjunction, when an object passes behind the Sun as seen from Earth, creates an observation gap that can last days or weeks, depending on the object's trajectory and brightness. For a faint comet already showing signs of unusual behavior, this gap becomes a black boxer period where anything could happen and we'd have no way of knowing. The comet could be disintegrating. It could be brightening dramatically. It could be intact and simply too close to the Sun's glare to see. We wouldn't know until it emerged, if it emerged. Models attempted to predict what would happen based on assumed nucleus sizes and compositions. If the nucleus was large and mostly rocky, thermal models suggested it would survive with minimal mass loss. If it was small and icy, the heat near perihelion could vaporize it completely, leaving nothing but a dispersing cloud of gas and dust. The uncertainty in nucleus size was enormous, ranging from a few hundred meters to several kilometers, a factor of 10 or more. And that uncertainty propagated through every prediction model, turning forecasts into guesswork. The phrase astronomers kept choosing was invisible interstellar traveler, somewhere behind the Sun's glare, hidden from every telescope humanity has built. An object from another star system was either surviving or dying, and we could do nothing but wait and wonder. What would emerge when the geometry finally allowed observation again? The wait felt like an eternity compressed into days. Let's get one thing straight: the Sun is not the gentle, life-giving star we like to imagine. Up close, it's a violent, chaotic beast. A roiling ball of plasma where temperatures reach millions of degrees and magnetic fields twist into configurations that store energy like loaded springs. When those springs snap, the results can be catastrophic for anything nearby. The coronal hole that opened in October 2025 was one of those events that make solar physicists break out in a cold sweat. Coronal holes are regions where the Sun's magnetic field opens up into space rather than looping back to the surface. These open field lines act like highways for solar wind, allowing plasma to escape into the solar system at high speed. A typical solar wind speed is around 400 kilometers per second. The wind pouring from this particular coronal hole was moving at 700 kilometers per second, nearly twice as fast, carrying more momentum, more energy, more potential for disruption. When solar wind at those speeds encounters a comet, the interaction becomes complex and violent. Comets don't have magnetic shields like Earth. They don't have a magnetosphere to deflect the charged particles. Instead, the solar wind slams directly into the coma, the cloud of gas and dust surrounding the nucleus, and strange physics takes over. The gas in the coma becomes ionized by solar ultraviolet radiation, creating a population of electrically charged molecules. These ions respond to magnetic fields, and the solar wind carries frozen-in magnetic field lines that drape around the comet like a cape. The result is a magnetostellar structure formed by the interaction between the solar wind's magnetic field and the ionized gas from the comet. This tail can extend millions of kilometers downstream away from the Sun, glowing faintly in the light of ionized carbon monoxide and other molecules. The tail isn't just a passive structure. Turbulence in the solar wind causes the tail to wave and flutter. Disconnection events can occur where the tail breaks off entirely and a new one begins to form. These interactions are visible from Earth with the right instruments, and they provide clues about both the solar wind conditions and the comet's gas production rate. But what happens when a comet encounters an exceptionally fast solar wind, while already stressed by intense solar heating near perihelion? History provides some terrifying examples. Comet Ison, discovered in 2012 and predicted to become spectacularly bright, disintegrated during its close pass by the Sun in 2013. Images from solar observing spacecraft showed the comet entering the perihelion region as a bright object and emerging as nothing but a dispersing cloud of dust. The nucleus apparently broke apart completely, unable to withstand the thermal and tidal stresses. Comet Lovejoy, a sungrazer that passed within 140,000 kilometers of the solar surface in 2011, somehow survived despite predictions it would be destroyed. Images captured the comet's tail extending millions of kilometers after perihelion, fed by massive gas production from the superheated nucleus. The survival of Lovejoy was unexpected and still not fully explains. Some combination of nuclear size, composition, and structural strength allowed it to endure heating that should have vaporized it entirely. 3I Atlas wasn't passing as close to the Sun as those extreme sunraises, but it was entering the region where solar influence becomes dominant. And it was doing so during a period of unusually intense solar wind. The question became whether the combination of factors thermal stress, plus radiative heating, plus solar wind pressure, plus possible prior fragmentation would be enough to destroy it. Some researchers proposed more exotic interactions. The electric comet model, promoted by a small group of plasma physicists, suggests that comets develop electrical charges as they interact with the solar wind, and that electrical forces, not just thermal sublimation, drive comet activity. Mainstream astronomy hasn't embraced this model, finding that conventional physics explains observations adequately without invoking electrical effects. But proponents point to phenomena like disconnection events in comet tails and rapid brightness changes as evidence that electrical processes play a role. The hypothesis extends further into fringe territory, with suggestions that strong solar wind events could induce charge separations in a comet's coma that might, under certain circumstances, cause explosive disruptions or trajectory changes beyond what's expected from simple outgassing. The evidence for these claims is contested, the theoretical framework incomplete, but the ideas circulate because they attempt to explain observations that don't quite fit standard models. When 3I Atlas disappeared during a major solar wind event, those promoting electric comet models saw potential confirmation of their ideas. Mainstream astronomers saw an unfortunate, but ultimately coincidental, overlap of events. What makes the situation more uncertain is that we don't actually know what 3I Atlas is made of. Spectroscopic observations before the disappearance were limited and didn't provide a complete compositional inventory. The comet could be water ice dominated like many solar system comets. It could be carbon monoxide ice dominated, which sublimates at much lower temperatures and could drive activity at greater distances from the Sun. It could be rich in silicates and poor in volatiles, more like an asteroid than a typical comet. Each composition would respond differently to solar heating and solar wind interaction. If the nucleus is extremely porous, almost like Eregio, with density barely higher than the gas in the coma itself, Thermal waves would penetrate deeply, heating subsurface ice and potentially causing the entire structure to disintegrate in a cascade of sublimation. If the nucleus has an insulating dust mantle covering most of its surface, gas production would be concentrated in a few active areas, creating jets that could spin up the nucleus or torque its rotation in unpredictable ways. If the nucleus is a contact binary to lobes held together by weak gravity-tidal forces, and thermal stress could pull it apart. The sun, in this scenario, becomes a kind of cosmic gatekeeper, a destructive force that tests every object passing through the inner solar system. Interstellar comets, having formed in different environments with possibly different structural properties than solar system comets, might be particularly vulnerable. They might be more robust, forged in conditions that made them tougher. We won't know until we see what emerges. The comparison to Comet Shoemaker-Levy 9 is instructive. That comet was torn apart by tidal forces during a close pass by Jupiter in 1992, breaking into more than 20 fragments that later crashed into the planet in a spectacular series of impacts. The tidal disruption happened because Jupiter's gravity gradient across the comet's diameter exceeded the comet's own self-gravity, literally pulling it apart. The Sun's tidal forces are much weaker at the distance where 3I Atlas passed, but a comet already weakened by thermal stress or prior fragmentation might succumb to forces that a healthy nucleus would easily resist. Did the Sun just reveal something terrifying about interstellar visitors? The answer depends on what we see when the comet emerges from conjunction. If 3I Atlas reappears intact, continuing on its hyperbolic trajectory with normal gas and dust production, the solar wind event becomes a footnote coincidence that sparked speculation but ultimately meant nothing. If the comet has disintegrated or vanished, we're left with haunting questions about whether interstellar objects are fundamentally more fragile than our models assume. Whether there's something about their formation or structure that makes them vulnerable to solar assault in ways we didn't predict. The cosmic clock is ticking, and astronomers around the globe are marking calendars, checking ephemerides, and preparing observation plans for the moment when 3I Atlas should become visible again. The timeline depends on several factors, including the comet's exact trajectory uncertain due to non-gravitational forces, its brightness which could have changed dramatically, and the observing geometry which determines how far from the Sun the comet needs to be before telescopes can detect it against the sky background. Current predictions suggest the comet should emerge from solar conjunction in late October or early November 2025, reaching sufficient solar elongation. The angular separation from the Sun as seen from Earth to be observable with specialized equipment. Initial recovery attempts will likely use space-based observatories that can block the Sun's light more effectively than ground-based telescopes. SOHO, the Solar and Heliospheric Observatory, has coronagraphs designed to create artificial eclipse, allowing observation of the region close to the Sun where comets often hide. STEREO, the Solar Terrestrial Relations Observatory, consisting of 2 spacecraft in solar orbit, provides different viewing angles that might catch the comet earlier than Earth-based observations. The Parker Solar Probe, humanity's closest approach to the Sun, follows an orbit that periodically brings it within the orbit of Mercury. through regions where solar wind speed and temperature reach extreme values. If the probe's trajectory happened to pass near 3I Atlas during the conjunction period, its instruments might have captured data about the comet in conditions no Earth-based telescope can observe. But Parker's science objectives focus on the solar corona and solar wind, not comets, and unless the comet happened to be in the probe's narrow field of view at the right time, we'll have no data from that critical period. Mission scientists have not announced any fortuitous encounters, suggesting the geometry didn't align or that the comet was too faint for Parker's instruments to detect against the bright solar background. What will the first recovery images show? Best case scenario. The comet appears as expected, perhaps slightly fainter due to dust loss, but otherwise intact with a visible coma and tail, indicating active sublimation of ice from the nucleus. The spectral signature would show familiar lines of water vapor, cyanogen, carbon monoxide, molecular fingerprints that confer comet composition. The tail length and structure would provide information about gas production rate and solar wind conditions in the post-conjunction period. Astronomers would measure the brightness, compare it to pre-conjunction values, and assess whether the comet lost significant mass during its closest approach to the Sun. Worst case scenario, nothing. Appears the sky remains empty where 3I Atlas should be, suggesting complete disintegration. The nucleus fragmented into pieces too small to detect individually or vaporized entirely, leaving only a dispersing cloud of gas that's too diffuse to show up as a distinct object. This outcome would be disappointing scientifically, but not unprecedented. Several comets have disappeared after close solar approaches, and their loss becomes a data point in our understanding of comet fragmentation physics. Between these extremes lie numerous possibilities. The comet could return as multiple fragments, a string of condensations along the orbit, indicating the nucleus split, but the pieces survived. Fragment streams are difficult to observe because each individual piece is fainter than the original nucleus, but they provide valuable information about nuclear structure and the mechanics of breakup. If 3I Atlas returns as fragments, analysts would measure these separation distances and velocities to reconstruct when and how the breakup occurred. Another possibility is dormancy. The comet could have exhausted its near-surface volatiles during the close solar pass, leaving a darkened crust that prevents further sublimation until solar heating cracks the crust or erosion exposes fresh ice. Dormant comets look like asteroids, showing no coma or tail, just a bare rock reflecting sunlight. If 3I Atlas goes dormant, we'd lose our ability to study its gas composition, but we'd gain information about surface processes and the formation of insulating mantles. The most intriguing scenario involves unexpected brightening. Sometimes comets fragment in ways that expose fresh, volatile-rich material to sunlight, causing sudden increases in gas production and brightness. A fragmenting nucleus can create new active areas, increasing the total sublimating surface area. If 3I Atlas fragments and brightens simultaneously, the comet that emerges might be more spectacular than the one that disappeared, though in fragmented form. It would likely fade quickly as the small pieces deplete their ice reserves. Spectral diagnostics will be critical. Observations before conjunction show the typical signatures of water and perhaps carbon monoxide, but a complete spectral inventory was never obtained. Post-conjunction spectroscopy might reveal species that weren't detected earlier either, because the comet wasn't producing them in significant quantities, or because we weren't looking at the right wavelengths. Oxygen emission lines would indicate water sublimation. Cyanogen points to carbon-nitrogen chemistry. Sodium and iron lines sometimes appear in comets and can indicate exposure of metallicrich, material from the nucleus interior amateur. Astronomers have a role to play in the recovery effort. A network of backyard telescopes distributed globally provides continuous sky coverage that professional facilities with their limited observing time and scheduled programs cannot match. If 3i Atlas brightens unexpectedly or fragments into widely separated pieces, amateur observers might be the first to notice. Crowdsourced astronomy has become increasingly important as digital cameras and software make it possible for dedicated amateurs to produce observations rivaling professional quality. There's a live cosmic mystery unfolding in real time, and everyone with a telescope in clear skies can participate. The comet could reappear at any moment, assuming it survived, or days could pass, then weeks with nothing visible until astronomers reluctantly conclude that 3i Atlas is gone destroyed by the sun. It came so far to visit. The uncertainty is maddening and exhilarating in equal measure. We sent no probe to intercept the comet. We have no way to actively search for it beyond pointing our telescopes at the predicted location and waiting. All we can do is watch and wonder and prepare for whatever emerges from the solar glare. The broader question haunts the astronomical community. If the nucleus is gone, do we still have 3i Atlas? Or is it just debris, now a dispersed cloud of dust and gas that once was an interstellar comet, but no longer qualifies as a discrete object? Philosophically, it echoes the ship of Theseus' paradox. If every plank of a wooden ship is replaced over time, is it still the same ship? If a comet fragments into 1,000 pieces, each piece following nearly the same orbit, carrying material from the original nucleus, are they collectively still the comet, or has the comet ceased to exist? There's no formal definition that resolves this question. It's a matter of convention and convenience, and different researchers will answer differently depending on their perspective. But the question matters because 3i Atlas represents something precious and irreplaceable, a sample of another star system. And losing it feels like more than just losing an astronomical target. It feels like losing a connection to something vast and distant, a thread linking us to the wider galaxy that got severed before we could fully grasp what we held. Let's get real for a minute. Why does any of this cosmic drama matter beyond the narrow confines of planetary science, journals, and astronomy conferences? Because humans are pattern-seeking creatures, hardwired to find meaning in correlation, to see connections even where none exist, and the simultaneous occurrence of a major solar event, the disappearance of an interstellar comet, and multiple large earthquakes on Earth triggered every alarm in our collective unconscious that screams, something is happening here. The mainstream scientific position on solar-terrestrial earthquake connections is clear and unambiguous. Earthquakes are driven by plate tectonics, by the slow, inexorable motion of lithospheric plates riding on the convecting mantle. by accumulated strain energy in the crust that eventually exceeds the frictional resistance holding faults locked. Solar activity has no plausible mechanism to trigger this release. Magnetic fields don't affect rock. Solar wind particles don't penetrate to Earth's surface. They're stopped by the magnetosphere and atmosphere. The thermal energy delivered by solar radiation is negligible compared to Earth's internal heat. Every analysis of earthquake catalogs looking for correlations with solar cycles or individual solar events has found nothing beyond what would be expected by chance. And yet, the correlations keep appearing in data sets, tantalizing patterns that don't quite reach statistical significance, but don't quite disappear either. Some researchers working at the margins of respectability continue to explore possible mechanisms. Could ionospheric disturbances caused by solar activity affect the electrical properties of fault zones? Could subtle changes in Earth's rotation, rate, or magnetic field orientation driven by solar wind momentum transfer modulate tectonic stress at levels too small to measure directly, but sufficient to tip a fault that's already near failure? Could there be magneto-hydrodynamic coupling between the ionosphere and conducting layers in the crust that transmits energy in ways we don't yet understand? These ideas face enormous skepticism because extraordinary claims require extraordinary evidence, and the evidence remains circumstantial at best. But the human mind doesn't operate on statistical significance thresholds. It operates on narrative, on stories that connect disparate events into coherent wholes. When the sun attacks, an earthquake strikes, and a comet vanishes, all in the same news cycle, the narrative writes itself. Even if the physics doesn't support it, the interstellar nature of 3I Atlas adds another layer of mystery and speculation. These objects come from outside our solar system, from environments we can barely imagine, formed from materials whose composition and isotopic ratios might differ from solar system norms. They're literally alien in the most precise sense of that word, and humanity has always projected its hopes and fears onto the alien and unknown. When Amuma exhibited acceleration that couldn't be immediately explained by standard comet outgassing, speculation erupted about artificial origin, about alien probes conducting reconnaissance, about technologies beyond our understanding. The simplest explanation remained natural processes, but the alien probe hypothesis captured public imagination because it satisfied narrative needs that dry scientific papers about carbon monoxide sublimation could never touch. 3I Atlas disappearing during a solar storm invites similar speculation. Did the comet carry something in code, in composition, that made it a target? Are we witnessing a cosmic quarantine protocol? The sun destroying potential threats from interstellar space before they can penetrate the inner solar system. The scientific absurdity of these ideas doesn't diminish their psychological appeal. We want the universe to contain mysteries deeper than orbital mechanics and spectroscopy. We want hidden meanings behind celestial alignments. We want comets to be more than dirty snowballs. We want them to be messengers, carriers of information or life or purpose. The panspermia hypothesis, the idea that life spreads through the cosmos on comets and asteroids, provides a scientific veneer for these desires. If comets carried the organic precursors that led to life on Earth, delivered during the heavy bombardment period billions of years ago, then every comet becomes a potential seed carrier, and interstellar comets become particularly precious because they might carry chemistry from biospheres around other stars. The destruction of 3I Atlas, if that's what happened, becomes the destruction of a biological sample, a library burned before we could read its contents. More exotic possibilities circulate in fringe communities. Crick universe proponents see the sun's interaction with the comet as evidence of plasma physics they claim mainstream science ignores. They point to the comet's unusual brightness variations, to the strong solar wind, to disconnection events in other comet tales, and argue these phenomena require electrical rather than gravitational and thermal explanations. The mathematics of their models rarely withstand scrutiny. Predictions often fail to match observations, but the intuitive appeal of electricity as a universal force, the visual drama of lightning and sparks, gives electric universe ideas a persistence that transcends their scientific shortcomings. Conspiracies inevitably emerge. Are space agencies hiding data from the Parker solar probes close passers-by the sun? Did instruments capture images or spectra of 3I Atlas during the conjunction period that officials chose not to release? What would motivate such secrecy? Perhaps the comet exhibited behavior that couldn't be explained, that challenged fundamental assumptions, that frightened people who understood the implications. Perhaps it fragmented in a manner inconsistent with natural processes, or emitted signals, or changed trajectory in ways that suggested control. These scenarios are vanishingly unlikely, bordering on impossible. But absence of evidence becomes evidence of conspiracy in minds predisposed to distrust official narratives. The psychological function of conspiracy theories is well studied. They provide control, the illusion of control in the face of random and chaotic events. They replace a universe of meaningless coincidence with a universe of hidden order and purpose. Even if that purpose is malevolent, better to believe in conspiracies than to accept that earthquakes strike randomly, that comets disintegrate without reason, that we're tiny specks of consciousness on a fragile world hurtling through an indifferent cosmos. The narrative of hidden knowledge and suppressed truth is more emotionally satisfying than the narrative of patient scientific investigation, slowly converging on tentative conclusions. But here's the thing: sometimes the universe does align in ways that defy probability. Sometimes coincidences are too perfect to dismiss, even when we can't establish causation. The October 2025 conjunctive events, solar storm and comet disappearance and earthquakes might be exactly that. A coincidence so improbable that it demands our attention, even if ultimately it means nothing. Or it might be the first hint of connections we don't yet understand. Couplings between geophysical systems and space weather that operate at levels below our current detection thresholds. Science progresses by investigating anomalies, not by dismissing them. The researchers exploring solar earthquake correlations are doing legitimate, if speculative, science. They'll probably find nothing, but the search itself is worthwhile. When 3I Atlas emerges from behind the sun, if it emerges, we may not recognize it. The comet that went in might not be the comet that comes out. And when astronomers publish their analyses of what they observe, when they present explanations grounded in physics and chemistry and orbital mechanics, some people will accept those explanations and move on. Others will continue searching for hidden meanings, for connections between the comet and the earthquakes and the solar storm that transcend material causation. Both responses aren't human. Both reflect deep needs to make sense of our place in a cosmos that offers more questions than answers. The sun did something terrifying, and a comet vanished, and the earth shook, and whatever truth underlies those events. We're left with wonder and unease in equal measure. While 3i Atlas plays cosmic hide-and-seek behind the sun, another comet is putting on a show. You can actually witness, assuming you know where to look and you're willing to wake up. Before dawn, or stay up late after sunset, meet Comet C 2025. A611, discovered by the Mount Levin Observatory in Arizona, and thus carrying the designation Levin. This icy traveler is approaching its own close encounter with the sun, reaching brightness levels that put it within range of binoculars or small telescopes, possibly even naked eye. Visibility for observers under dark skies, away from light pollution. The next 2 weeks represent the optimal viewing window. Lemon's perihelion-its closest approach to the sun is scheduled for mid-November 2025, but the geometry of its orbit brings it to maximum visibility from Earth slightly before perihelion, when it's still far enough from the sun's glare to observe comfortably. The comet is currently visible in the pre-dawn eastern sky, rising a few hours before the sun, glowing with the soft, fuzzy light characteristic of an active comet with a well-developed coma and possibly a short tail. Current magnitude forecasts place Lemon between magnitude 4 and magnitude 5, right at the threshold of naked eye visibility. The human eye can typically see objects down to magnitude 6 under good conditions, so magnitude 4 should be easily visible away from city lights, though pinpointing it without binoculars requires knowing exactly where to look. The comet is currently passing through the constellation Cancer, moving eastward against the background stars, and finder charts available online show its path relative to easily recognizable star patterns. Observing comets requires patience and dark skies. Unlike planets, which appear as distinct points or disks, comets are diffuse objects, their light spread across an extended area. This diffuse nature makes them more sensitive to light pollution and sky conditions than compact objects of similar integrated brightness. A magnitude for comet will vanish completely in bright suburban skies where magnitude 4 stars remain easily visible. Success requires traveling away from urban areas to locations where the Milky Way is visible overhead, where the sky darkness allows your eyes to detect extended low-surface brightness objects. Binoculars are the ideal instrument for comet observing. They provide enough magnification to concentrate the comet's light while maintaining a wide field of view that makes finding and tracking the object easier. 7 by 50 binoculars are common size, owned by many amateur astronomers and nature observers work particularly well. Mount them on a tripod if possible to eliminate handshake and allow longer viewing periods without fatigue. The comet will appear as a small fuzzy patch, distinctly interstellar, possibly with a hint of green color from emission by diatomic carbon molecules in the coma. Telescopes can reveal more detail, showing the coma structure, any jets or fans of material emanating from specific active regions on the nucleus and the tail, if one has developed sufficiently. But higher magnification narrows the field of view, making the comet harder to locate initially and harder to keep centered as Earth's rotation carries it across the sky. Many experienced comet observers prefer binoculars for aesthetic reasons. The wide-field view shows the comet in context against star fields and the Milky Way, emphasizing its nature as a temporary visitor moving through more permanent celestial scenery. Early observations of Lehmann revealed something that makes comet scientists nervous and excited in equal measure. The brightness wasn't following prediction models perfectly. Comets are notoriously difficult to predict because their brightness depends on factors we can't measure directly, like nuclear size, composition, rotation, state, surface properties, and Dust-to-gas ratio. Models make assumptions about these parameters based on statistics from other comets, but individual comets often deviate from average behavior. Lehmann showed periods where it brightened faster than expected, followed by plateaus where the brightness remained nearly constant despite decreasing distance to the Sun. These deviations could indicate several phenomena. Outbursts activity, where a sudden exposure of fresh, volatile material creates a temporary increase in gas and dust production, can cause rapid brightening. Rotation of the nucleus, bringing different hemispheres into sunlight. If one hemisphere is more active than the other, creates periodic brightness variations, or more ominously, the deviations could signal the early stages of fragmentation, where the nucleus begins to break apart under thermal or tidal stress. Fragmentation is the hidden danger that haunts every comet prediction. A comet can be brightening, normally following its expected curve toward perihelion, looking healthy in every respect, and then suddenly it starts to come apart. The process can be rapid or gradual. Sometimes a large chunk splits off and forms a separate condensation visible near the main nucleus. Sometimes the entire nucleus disintegrates into a cloud of small fragments that individually are too faint to see, but collectively can create a dramatic increase in total brightness as their combined surface area drives enhanced sublimation. The physics of fragmentation involves mechanical strength, thermal stress, and spin state. Comet nuclei are weak structures, more like compacted snow than solid rock, held together primarily by their own feeble gravity, supplemented by tensile strength from ice cementing and possibly organic tars. When the Sun heats one side of the nucleus, thermal expansion creates stress. If the nucleus is spinning, centrifugal forces add mechanical stress, and jets create torques that can spin the nucleus up to faster rotation rates. At some point, the accumulated stress exceeds the material strength, cracks propagate, and the nucleus splits. Lehmann's sublimation science adds another layer of complexity. The comet appears to be driven by carbon monoxide or carbon dioxide sublimation as much as or more than water sublimation. These molecules are more volatile than water, meaning they turn from solid to gas at lower temperatures and greater distances. From the Sun, a carbon monoxide-driven comet can be active far beyond the snow line where water ice remains frozen, producing a coma and tail while still in the outer solar system. As the comet approaches perihelion and temperatures rise, water sublimation eventually takes over, often creating a transition in activity, patterns and brightness behavior. The tail interactions with solar wind provide another observational opportunity. Lehmann's ion tail, if it develops one, will point directly away from the sun, blown by the solar wind like a windsock. The dust tail follows a curved path, particles pushed by solar radiation pressure, but retaining the orbital motion they had when released from the nucleus. These two tail types, ion and dust, often separate into distinct structures visible in photographs. The ion tail appears bluish from carbon monoxide ion emission, straight and sometimes featuring streamers and knots caused by magnetic field irregularities in the solar wind. The dust tail appears yellowish-white from reflected sunlight, broader and more diffuse, curving gently away from the nucleus dot. Comparing lemon to 3I Atlas highlights fundamental differences between solar system native comets and interstellar visitors. Lemon formed 4.6 billion years ago in the disk of gas and dust surrounding the young sun, probably in the region beyond Neptune, where temperatures were cold enough for water and other volatiles to condense as ice. Gravitational perturbations from the giant planets eventually scattered it into the Oort, clouded vast, spherical reservoir of comets surrounding the solar system at distances up to 100,000 astronomical units. Something perhaps the gravitational influence of a passing star or a giant molecular cloud-perturbed lemon's orbit, sending it falling back toward the sun on the journey we're now observing. Its composition reflects primordial solar system chemistry, the isotope ratios and molecular abundances present in our local region of the galaxy. 4 billion years ago, 3I Atlas formed somewhere else, around a different star in conditions that might have been similar or radically different. The temperature and pressure in that protoplanetary disk, the abundance of heavy elements, the radiation environment, the timing of planet formation, all these factors influence comet composition and structure. By comparing interstellar comets to solar system comets, we're essentially comparing samples from different stellar nurseries, looking for commonalities that reveal universal processes and differences that highlight local variations. Lemon serves as a real-time reminder of how fragile comets are. Every comet is a gamble against disintegration. Most survive their perihelion passage, lose some mass to sublimation, retreat back to the outer solar system or beyond, and remain intact. Some fragment dramatically, providing spectacular shows as multiple nuclei and expanding dust clouds brighten and fade. A few vanish completely, destroyed so thoroughly that tracking them afterward becomes impossible. Watching Lemon during its peak visibility window isn't just about appreciating a beautiful celestial sight. It's about witnessing a object that has endured billions of years in the deep freeze of the Oort cloud and is now running a gauntlet of solar heat and radiation that might or might not end in its destruction. Comets tend to arrive in bunches, or at least that's how it seems to observers tracking these icy visitors. The reality is more prosaic. At any given time, numerous comets orbit the sun at various distances, most too faint to observe without large telescopes, a few bright enough to attract amateur attention, and very rarely one spectacular enough to become visible to the naked eye and enter public consciousness. The clusters we perceive result from observational bias and the statistical nature of comet discoveries, but they still create periods where comet watchers have multiple targets to choose from. 22.5 is shaping up as one of those periods, alongside Lemming and the vanished 3I Atlas, another comet designated C 2025, to Swan has entered the catalogue. Swan refers to the solar wind and a Satrapi's instrument aboard the SOHO spacecraft, which observes the sky in ultraviolet wavelengths sensitive to hydrogen emission. Comets produce enormous hydrogen clouds, neutral hydrogen atoms created when water molecules break apart under solar ultraviolet radiation. These clouds are invisible to optical telescopes but glow brightly in specific UV wavelengths, and Swan can detect them at vast distances, sometimes spotting comets months before they become visible to ground-based observers. CE 2025 Edward Swan was discovered through its hydrogen corona, that immense invisible cloud surrounding the visible coma. Follow-up optical observations confirmed the discovery and allowed trajectory calculations. The comet is following an elongated elliptical orbit that will bring it to perihelion in early 2026, well after Le Mans' close approach, but soon enough to maintain interest among comet observers preparing their equipment and observation plans. Early brightness estimates for Swan suggest it might reach magnitude 6 or 7 at perihelion, making it a binocular object, but probably not naked eye, visible except under exceptional circumstances. The predicted brightness depends on assumptions about nuclear size and activity level, both of which remain uncertain. Some comets discovered by Swan have exceeded expectations, brightening significantly as they approach the Sun. Others have disappointed, remaining faint and diffuse despite hopeful predictions. The only way to know is to watch and wait. One intriguing possibility associated with new comets involves meteor showers. When a comet approaches the Sun, it sheds dust that spreads along its orbital path, creating a stream of particles. If Earth's orbit intersects this dust stream, the particles slam into our atmosphere at high velocity, typically 30 to 70 kilometers per second, and vaporize in bright streaks we call meteors or shooting stars. Most meteor showers we observe annually, like the Perseids in August or the Geminids in December, result from Earth passing through well-established dust trails left by comets that have made multiple perihelion passages, depositing dust over centuries or millennia. New comets making their first passage through the inner solar system can produce unpredictable meteor activity. The dust distribution along the orbit hasn't been smoothed out by repeated passages and planetary perturbations. Fresh outbursts might create dense clumps of particles. If Earth happens to pass through one of these clumps, meteor rates could spike dramatically, creating a meteor storm with hundreds or thousands of visible meteors per hour. These events are rare and difficult to predict because they depend on the exact spatial distribution of dust, which we can't measure directly. SWAN's orbit will be calculated precisely in the coming months, and astronomers will determine whether any potential Earth-dust stream intersections might occur. Even a low possibility of a meteor shower gets comet and meteor enthusiasts excited. Observing a meteor storm is a bucket list experience celestial. Fireworks displayed that happens perhaps once or twice per generation. The meteors radiates from a point in the sky called the radiant converging perspective lines, created by parallel particle trajectories entering the atmosphere. During a storm, the entire sky appears to rain meteors, streaks of light appearing in all directions, overwhelming the senses in a way that photographs can never fully capture. But for every comet that brightens and performs as hoped, several others fizzle. The history of comet astronomy is littered with predictions that failed, with objects expected to become great comets that instead remained faint and unremarkable. Comet Kohoutek in 1973 was predicted to become one of the brightest comets of the century, but barely reached naked-eye visibility, disappointing millions who had been promised a spectacular show. Comet Ison in 2013 was supposed to survive perihelion and brighten dramatically, but instead disintegrated. These failures teach humility and remind us how much we still don't understand about comet physics. The comparison between swan and lemons brightness curves will eventually provide useful scientific data. Two comets observed simultaneously under similar solar conditions allow direct comparison of activity levels and sublimation physics. Differences in brightness at comparable distances from the Sun indicate differences in nucleus size, composition, or surface properties. If one comet is water-dominated and the other carbon monoxide-dominated, their activity profiles will diverge in characteristic ways. If one fragments and the other doesn't, we gain clues about structural differences that determine fragmentation susceptibility. Using swan and lemon as foils creates narrative tension. Many comets fail, so will 3I Atlas fail too? Is there something about the current solar environment that makes comet survival less likely? The October 2025 coronal hole event could have been a one-time fluke, or it could signal a period of enhanced solar activity that threatens any comet passing through the inner solar system. The Sun's 11-year activity cycle is approaching solar maximum, the period when sunspots and coronal mass ejections become frequent, when solar wind speeds and magnetic field strengths increase. Comets approaching perihelion during solar maximum face harsher conditions than those arriving during solar minimum. Comet fragmentation history provides sobering statistics. Comet Shoemaker-Levy 9's tidal disruption by Jupiter in 1992, followed by the spectacular impacts in 1994, demonstrated how thoroughly a comet can be destroyed by gravitational and tidal forces. Comet 73P Schwarzmann-Walkman 3 fragmented during its 1995 apparition, splitting into multiple pieces that separated over subsequent years. By its 2011 return, the comet had broken into more than 60 identified fragments. A debris field spread along several thousand kilometers of orbit. Some fragments remained active, producing small comet. Others appeared dormant, their volatiles depleted or sealed beneath inactive crusts. These fragmentation events matter for predicting space hazards. A single large comet nucleus poses minimal risk to Earth because the probability of the few kilometer-wide nucleus hitting our planet is vanishingly small. But a fragmenting comet creates dozens or hundreds of pieces, each capable of atmospheric entry. And while the individual pieces are smaller and less destructive than the original nucleus, the probability that one of them intersects Earth's path increases. Most comet fragments burn up harmlessly in the atmosphere or miss Earth entirely. But the risk calculation changes when you're dealing with distributed debris rather than a single object. Foreshadowing the 2060 comet event, predicted to be the brightest comet apparition of the century, puts current observations in perspective. Comets are the solar system's chaotic clock, appearing unpredictably, brightening erratically. fragmenting without warning. They mark time in human consciousness differently than the regular motions of planets and stars. A generation remembers Halley's Comet in 1986, a disappointing view for most but culturally significant. The generation before remembers Comet Hale-Bopp in 1997. Visible to the naked eye for months, bright enough to see from city centers. The current generation may remember Lemon or Swan or Three-Eye Atlas, assuming any of them survive and brighten sufficiently. Are we in a cluster period of unusual comet appearances? Statistical analysis of comet discovery rates over decades shows fluctuations that might represent real clustering or might simply reflect improvements in detection technology. More telescopes, scanning more sky at greater sensitivities, naturally find more comets. The Atlas survey that discovered Three-Eye Atlas exists specifically to find near-Earth objects and finds comets as a bonus. The Catalina Sky Survey, Mount Lemmon, observatories, pan-stars in Hawaii, all these automated systems constantly watch for anything that moves. And comets move, so they get found. But there's a tantalizing hint in the data that the Oort cloud, that distant reservoir of comets, might experience perturbations that send showers of comets falling toward the inner solar system, passing stars. Gravitational interactions with giant molecular clouds in the galaxy. Even the vertical oscillation of the solar system through the galactic plane as it orbits the Milky Way center. All these could shake comets loose. If real, these comet showers would occur on timescales of millions of years, far too long for human observation to detect directly. But buried in the geological record, evidence of impact clustering might reveal these ancient storms of comets that battered the inner solar system during the dinosaurs' reign, or even earlier in Earth's history. While astronomers scan the skies for comets and track solar wind, another kind of cosmic race unfolds in laboratories and ground stations here on Earth. In 2025, China announced completion of the world's longest quantum communication linker. 12,900 kilometers network connecting Beijing, two distant ground stations through satellite relays, and claimed the system provides effectively unhackable data transmission. The announcement represents a milestone in the quantum information revolution. And if the system works as advertised, it changes the landscape of global communications and cybersecurity in ways that extend far beyond immediate military or commercial applications. Quantum key distribution, the underlying technology, exploits fundamental properties of quantum mechanics to detect eavesdropping. The basic principle is elegant and strange in equal measure. Information gets encoded in the quantum states of photon singar, particles of light transmitted through optical fibers or through space between satellites and ground stations. The quantum non-cloning theorem guarantees that these states cannot be copied perfectly. Any attempt to measure or intercept the photons necessarily disturbs them in detectable ways. This means two parties sharing a quantum communication channel can generate encryption keys and know with certainty whether anyone tried to intercept those keys during transmission. The process begins with entangled photon pairs of particles created simultaneously and sharing a quantum connection such that measuring properties of one photon instantly affects the other, regardless of the distance separating them. This phenomenon, which Einstein famously called spooky action at a distance, has been verified in countless experiments and forms the basis for several proposed quantum technologies, including quantum computing and quantum teleportation. 4. Quantum key distribution. Entangled photons allow two parties to establish shared random numbers that can be used as encryption keys. Hardware implementation requires extraordinary precision. Photons must be generated, entangled, transmitted, and detected with minimal loss and maximal fidelity. Optical systems must align satellite transceivers with ground stations across hundreds or thousands of kilometers while compensating for atmospheric turbulence, satellite motion, and Earth's rotation. Single photon detectors must register individual particles arriving at rates of thousands or millions per second, distinguishing real signals from background noise and detected dark counts. Error correction protocols must account for inevitable imperfections while still guaranteeing security. China's system uses the Meteos satellite, launched in 2016 and named after an ancient Chinese philosopher. The satellite orbits at roughly 500 kilometers altitude, passing over ground stations in a sun-synchronous orbit that provides regular communication windows. During each pass, lasting several minutes, the satellite distributes entangled photons to pairs of ground stations, allowing them to establish shared encryption keys. These keys then secure conventional data transmission using standard encryption algorithms, with the quantum channel guaranteeing that the keys themselves weren't compromised. The recent expansion to 12,900 kilometers represents a significant engineering achievement. Earlier demonstrations covered shorter distances or relied on trusted relay stations that theoretically could be compromised. The new system chains quantum links across multiple satellite passes and ground stations, creating end-to-end security. Across continental scales, according to Chinese researchers, the network already serves government and financial institutions, protecting communications against both current and future decryption threats. That last point matters crucially. Current encryption systems, the ones protecting everything from bank transactions to classified government communications, rely on mathematical problems that are computationally difficult to solve with classical computers. Factoring large numbers, computing discrete logarithms, these tasks require so much computational time that breaking encryption becomes impracticable, even with the fastest supercomputers available. But quantum computers, if built at sufficient scale, could solve these problems efficiently, rendering current encryption obsolete. Data encrypted today and captured by adversaries could be decrypted years or decades in the future, once quantum computers mature. Quantum key distribution offers protection against this harvest now. Decrypt, later threat, because the security doesn't rely on computational difficulty, but on fundamental physics. Western nations, particularly the United States and European countries, view China's progress in quantum communications with concern. The MIT Technology Review Quantum Index in 2025 ranks China ahead in several quantum technology metrics, including quantum communications and quantum sensing. American research programs are working to catch up with the Department of Energy funding, quantum network test beds, and DARPA exploring space-based quantum communication architectures. But China's early lead and substantial government investment have created a quantum gap that worries defense planners and technology strategists that the policy implications extend beyond simple technological competition. If quantum communication networks become the backbone of future secure communications, nations without access to the technology face potential information disadvantage. International agreements governing quantum technology development remain nascent. Questions about export controls, technology transfer, and standardization remain unresolved. Some researchers advocate for open collaboration and shared development of quantum networks as global infrastructure, similar to how the Internet developed as an international resource. Others push for competitive advantage and restricted access, viewing quantum superiority as a strategic asset, too valuable to share. Could space-based quantum networks become the backbone of the future Internet? The vision involves constellations of quantum satellites providing global coverage, ground stations in every major city, and quantum repeaters extending range beyond direct line-of-sight limits. Data would travel encrypted by quantum keys that refresh continuously, immune to intercession, resistant even to future technologies we haven't yet imagined. The system would integrate with existing fiber optic networks, providing a hybrid classical quantum infrastructure where quantum channels distribute keys and classical channels carry bulk data. Conspiracies naturally emerge around technologies this advanced and this secret. Quantum key distribution systems require extensive testing and calibration processes that generate data about photon transmission statistics, detector efficiency, and error rates. Most of this data remains classified or proprietary. Chinese publications describe the system's capabilities in general terms but omit engineering details that would allow independent verification or replication. Western intelligence agencies undoubtedly monitor the program closely, using signals, intelligence, and other means to assess its actual capabilities versus public claims. This opacity feeds speculation about whether the system works as advertised, or whether vulnerabilities exist that aren't being disclosed. Some worry about state surveillance, but the government controlling a nationwide quantum communication network has unprecedented ability to monitor who communicates with whom, even if the content remains encrypted. Metilitate the information about communication patterns rather than communication content often reveals as much as the messages themselves. Traffic analysis can identify social networks, track movements, predict behavior. A quantum network that logs every connection, every photon transmission, every key generation event creates a surveillance infrastructure of staggering scope. The tying to the 3I Atlas narrative rests on an interesting parallel. Just as comets carry messages from other star systems, sent coded not in language, but in chemistry and isotope ratios, humans now build systems to carry unbreakable encoded messages across our own planet. Both represent information that survives hostile environments. Comet chemistry, surviving interstellar space and solar heat. Quantum keys, surviving active adversaries trying to intercept them. Both push the boundaries of what's possible. Comets as natural information carriers shaped by billions of years of physics. Quantum networks as artificial information carriers shaped by decades of engineering. Unknowns remain numerous. Current quantum key distribution rates, typically measured in kilobits per second, lag far behind classical communication speeds measured in gigabits or terabits per second. Scaling quantum networks to handle internet-level traffic requires either dramatic improvements in photon transmission and detection efficiency or fundamentally new approaches to quantum networking. Decoherence, the loss of quantum properties due to environmental interactions, places fundamental limits on how long quantum states can be maintained and how far they can be transmitted. Satellites help extend range by operating in the vacuum of space above most of the atmosphere, but atmospheric turbulence at ground stations still degrades performance. Endpoint security presents another challenge. Quantum key distribution guarantees secure key transmission, but the keys must ultimately be used by classical computers to encrypt and decrypt data. If those computers are compromised through malware, physical access, or side-channel attacks that monitor electromagnetic emissions or power consumption, the unbreakable quantum keys become irrelevant. Security is only as strong as the weakest link, and in any real system, weak links proliferate. Science occasionally produces discoveries so unexpected, so contrary to intuition, that they force us to reconsider fundamental assumptions about what's possible. The announcement that synthetic biologists have engineered yeast to convert human urine into bone mineral hydroxyapatite represents one of those discoveries. The potential applications range from medical to ecological, and the deeper implications touch on questions of waste, value, and the surprising ways that biological systems can be reprogrammed to transform one substance into another. Urea, the primary nitrogen-containing component of urine, serves as a waste product in mammalian metabolism. When proteins break down in the body, amino acids get metabolized, and the nitrogen they contain must be excreted. Aquatic animals excrete ammonia. Directly a simple and energetically cheap solution when you live in water that dilutes and carries away the toxic compound, land animals face a challenge. Ammonia is too toxic to accumulate, but water conservation matters. So terrestrial animals evolved more complex solutions. Birds and reptiles produce uric acid, a relatively insoluble compound that precipitates out and can be excreted as a paste, minimizing water loss. Mammals produce urea, soluble enough to transport in water but less toxic than ammonia, excreted in liquid urine that represents a compromise between water conservation and waste removal. Humans produce roughly 1 to 2 liters of urine daily, depending on fluid intake and metabolic rate, containing about 20 to 30 grams of urea. That's roughly 10 kilograms of urea per person per year, multiplied by 8 billion people globally, giving roughly 80 million metric tons of urea excreted annually. Currently, this urea ends up in sewage systems, where it's broken down by bacteria or released into the environment. The new synthetic biology approach asks whether this waste stream might be converted into something valuable. Hydroxyapatite is the mineral component of bone and teeth, a calcium phosphate compound with the formula KPOG. It provides the hardness and structural integrity that allows bones to support body weight and protect organs. Natural bone is a composite material, hydroxyapatite crystals, embedded in a collagen protein matrix, combining the hardness of mineral with the flexibility and toughness of organic fibers. Medical applications require pure hydroxyapatite for bone grafts, dental implants, and reconstructive surgery. Currently, hydroxyapatite get synthesized through chemical processes or harvested from animal bones. Both approaches have limitations: impurity, crystal structure, and production cost. The engineered yeast approach works through metabolic pathway engineering. Researchers identified the series of enzymatic reactions needed to convert urea into the chemical precursors of hydroxyapatite, then inserted genes encoding those enzymes into yeast cells. The yeast norm Saccharomyces cerevisiae, commonly used in brewing and baking, now contain synthetic metabolic pathways that don't exist in nature. When fed urine as a nitrogen source and provided with calcium and phosphate ions, the yeast cells produce hydroxyapatite crystals that precipitate out and can be harvested. The mechanism involves multiple steps. Urease enzyme breaks urea into ammonia and carbon dioxide. The ammonia gets incorporated into amino acid synthesis pathways, while the carbon dioxide and additional calcium and phosphate ions undergo mineralization reactions that form hydroxyapatite. The precise crystallography of the product decide shape and purity of the hydroxyapatite crystals depends on reaction conditions, including pH, temperature, ion concentrations, and the genetic programming of the yeast pathways. Early results show promise, producing hydroxyapatite with properties similar to bone mineral, but significant optimization remains before the process becomes practical for medical applications. Current efficiency and yield rates limit immediate applications. The yeast produces hydroxyapatite at concentrations too low for commercial viability, requiring large bioreactor volumes to generate meaningful quantities. Purification challenges arise because the hydroxyapatite must be separated from yeast cells, growth medium components, and metabolic byproducts. Purity matters critically for medical use. Foreign proteins or bacterial endotoxins in implanted hydroxyapatite could trigger immune responses or infections. Achieving medical-grade purity from a biological production system requires rigorous quality control and purification protocols. Nevertheless, the potential is transformative. Bone fractures affect millions of people annually, and while most heal naturally, complex fractures or bone loss due to disease or trauma often require grafts or synthetic materials to support healing. Current bone graft materials include autografts harvested from the patient's own body, allografts from cadavers, and synthetic ceramics. Each option has drawbacks. Autografts require additional surgery to harvest the graft tissue. Allografts carry small risks of disease transmission and immune rejection. Synthetic ceramics sometimes fail to integrate well with natural bone. Hydroxyapatite produced biologically from waste materials could provide an abundant, cost-effective alternative if production and purification challenges get solved. Dental implants represent another major market. Hydroxyapatite coatings on titanium implants improve osseointegration, the bonding between implant and jawbone. Current coatings use hydroxyapatite produced through high-temperature chemical sintering, an energy-intensive process. Biological production at room temperature in aqueous solution would reduce energy costs and carbon footprint, while potentially creating more bone-like crystal structures that integrate better with living tissue. Ecological benefits extend beyond the direct use of the material. Urea in wastewater contributes to eutrophication when released into rivers and coastal waters. Excess nitrogen stimulates algal growth, leading to blooms that deplete oxygen and create dead zones. Capturing urea and converting it to solid mineral removes nitrogen from the waste stream, reducing environmental impact. The process represents waste valorization, the principle of treating waste as a resource rather than a disposal problem. Controversies naturally emerge around using human waste in medical materials. Cultural taboos about urine and feces run deep. Even though intellectually we understand that purified compounds have no memory of their origin, the calcium atoms in hydroxyapatite produced from urine are identical to calcium atoms from any other source. The material, once purified, carries no trace of waste beyond the historical fact of its production pathway. Yet psychological resistance remains. Would patients accept bone grafts or dental implants produced from urine? Would regulatory agencies approve such materials for human use? These questions touch on cultural values and risk perception more than technical feasibility. Astronaut. Applications provide perhaps the most compelling use case. Mars colonists or long-duration space missions face resource constraints that make every recycling opportunity valuable. Crew members will produce urine daily regardless, and that urine contains nitrogen and other elements that must be processed and either recycled or disposed of. Converting urine into usable hydroxyapatite for medical purposes or structural materials kills two birds with one stone, managing waste and producing useful products. The closed-loop life support systems needed for space exploration push designers toward maximal recycling and minimal waste. Your waste could literally save your life if a bone fracture on Mars requires a graft and the only available hydroxyapatite was produced from crew urine. Big pharma resistance to circular biotech adoption represents a predicted rather than demonstrated conspiracy. Pharmaceutical and medical device companies profit from current production methods and supply chains. Disruptive technologies that threaten existing business models face resistance regardless of their technical merit. Whether this resistance materializes for urine-derived hydroxyapatite depends on factors including production costs, scalability, regulatory pathways, and intellectual property landscapes. If the technology can be patented and controlled by established players, adoption becomes more likely. If it threatens to commoditize a high-margin product, resistance becomes more likely. The deeper takeaway transcends any specific application. Nature wastes nothing. Nutrients cycle through ecosystems. One organism's waste becomes another's food. Energy flows and elements circulate. Humans evolved in cultures where waste disposal was simpler, because population densities were low and natural processes degraded and recycled most waste products. Industrialization and urbanization broke these cycles, creating waste streams that overwhelm natural recycling capacity. Synthetic biology offers tools to rebuild those cycles, artificially engineering organisms to fill ecological niches that don't exist naturally but that serve human needs. Converting urine to bone mineral is just one example. The same principles apply to converting carbon dioxide to fuel, plastic waste to biodegradable polymers, agricultural runoff to valuable chemicals. We're learning to close loops that our technological development opened, catching up to the circular economy that nature perfected over billions of years. Animal behavior provides endless fascination because it reflects cognitive and emotional states we recognize from our own experience, yet manifests in creatures whose minds remain alien to us. Contagious yawning, the phenomenon we're witnessing. Someone yawn triggers the irresistible urge to yawn yourself, seemed until recently to be limited to humans and a few other highly social mammals like chimpanzees and dogs. The publication of a study demonstrating contagious yawning in zebrafish challenges that assumption and raises puzzling questions about the evolutionary origins and neural mechanisms underlying this behavior. Zebrafish, small freshwater fish, native to South Asian rivers and popular in both scientific research and home aquariums, have become model organisms for studying vertebrate development and behavior. Their embryos are transparent, allowing researchers to watch organs form in real time under microscopes. Their genetics are well characterized, with tools available for manipulating genes and observing the results. They're small, cheap to maintain, and produce hundreds of offspring, making them ideal for large-scale experiments. But nobody expected them to yawn contagiously. The experimental setup involved placing zebrafish in adjacent tanks where they could see each other through transparent walls. Researchers induced yawning in one fish through oxygen deprivation, a known trigger for yawning in many species. Cameras recorded the behavior of both the yawning fish and the observers. Analysis revealed that observer fish yawned significantly more frequently after witnessing a neighboring fish yawn with timing. Correlations suggesting genuine contagion, rather than coincidental yawning triggered by shared environmental conditions. Why is this shocking? Contagious yawning was thought to require mirror neurons or similar neural circuits that allow an animal to mentally simulate the actions and states of others. These circuits, concentrated in primate brains and suspected in certain social mammals, provide the neural basis for empathy, imitation learning, and theory of mind. Fish brains lack the cortical structures where mammalian mirror neurons reside. Their neural organization is fundamentally different, simpler in some respects, though certainly not simple overall. The presence of contagious yawning in zebrafish suggests either that the behavior doesn't require the sophisticated neural machinery we assumed, or that convergent evolution produced similar circuits in fish through entirely different anatomical pathways. Neural circuits underlying yawning in any species remain incompletely understood. The act itself involves coordinated contraction of muscles in the jaw, face, throat, and respiratory system, producing the characteristic gaping mouth and deep inhalation, followed by slower exhalation. The behavior appears involuntary once triggered, resistant to conscious suppression despite social contexts where yawning might be inappropriate. Multiple triggers exist, including fatigue, boredom, low oxygen, and the sight of others yawning. The diverse triggers suggest multiple neural pathways converging on a common motor output in humans. Contagious yawning increases during childhood development, peaks in young adulthood, and shows correlation with empathy measures. People scoring high on empathy questionnaires yawn more readily when watching others yawn. Individuals with autism spectrum disorders, who often struggle with social cognition and empathy, show reduced contagious yawning. These correlations support The hypothesis that contagious yawning relies on neural systems involved in social cognition and emotional resonance. Finding the same behavior in zebrafish creatures we don't typically credit with empathy or sophisticated social cognition challenges. This neat story, the evolutionary mystery, deepens when considering the taxonomic distribution. Contagious yawning appears in humans, chimpanzees, bonobos, dogs, and now zebrafish. It's absent or hasn't been demonstrated in many species tested, including cats, horses, and most birds. The scattered distribution across the animal kingdom suggests either multiple independent origins of the behavior or an ancient origin with subsequent loss in many lineages. Neither explanation is entirely satisfying. Convergent evolution of something as specific as contagious yawning in mammals and fish seems unlikely unless the behavior serves an important function we're missing. Ancient origin requires explaining why so many species lost it. Hypotheses about function vary widely. One proposal suggests contagious yawning serves group coordination, synchronizing states of arousal or attention across social groups. If one individual detects a change in environmental conditions that triggers yawning, perhaps signaling a transition from alertness to rest, spreading that signal through the group helps coordinate collective behavior. Fish schools certainly require coordination. They move as units, turning simultaneously, maintaining precise spacing, responding to threats with synchronized evasive maneuvers. Could contagious yawning be part of the behavioral toolkit that enables this coordination? Another hypothesis focuses on stress relief and social bonding. Yawning might serve to regulate stress hormones or reset neural states under social stress conditions. Seeing others yawn and yawning in response could create a feedback loop that helps groups collectively manage tension. Zebrafish are social animals at school in nature, and social dynamics involve dominance, hierarchies, mate competition, and predator vigilance. Perhaps contagious yawning plays a role in maintaining group cohesion under stress. The controversy centers on whether the behavior observed in zebrafish genuinely qualifies as yawning rather than some other jaw movement or gill action being misclassified. Fish don't breathe air under normal circumstances, so the respiratory component of mammalian yawning has no direct analog. The gaping mouth movement observed in zebrafish could serve different physiological functions related to gill ventilation or feeding. Critics argue that, without clear evidence, the fish behavior shares the same neural triggers and physiological consequences as mammalian yawning. Calling it contagious yawning anthropomorphizes as superficially similar but functionally distinct behavior. Proponents counter that the behavior shares key features with mammalian yawning, including involuntary nature, stereotyped motor pattern, triggering by hypoxia, and now demonstrated social contagion. The neural pathways may differ between fish and mammals, separated by hundreds of millions of years of evolution. But if the behavior serves similar functions and responds to similar triggers, the term yawning applies legitimately. Biology is full of convergent evolution where different structures serve similar functions. Bird wings and bat wings are anatomically distinct but functionally equivalent. Perhaps fish yawning and mammalian yawning represent convergent solutions to similar behavioral or physiological challenges. Speculation extends into deeper biological territory. Could yawn contagion represent a universal signal an ancient communication channel that predates more sophisticated social cognition. Perhaps the basic neural circuitry that makes yawning contagious evolved early in vertebrate history, preserved across hundreds of millions of years because it serves fundamental coordination functions in social species. This would require the behavior to provide significant fitness benefits to improve survival or reproduction, enough that natural selection maintains it despite the costs of the neural machinery required. The fringe possibility, rarely voiced in academic contexts but whispered in conference hallways, asks whether synchronization phenomena might extend beyond individual species, perhaps even across kingdoms of life. Yawn contagion, as currently understood, operates through sensory perception. Seeing or hearing someone yawn triggers neural pathways that produce yawning. But broader synchronization in nature occurs through mechanisms we're only beginning to understand. Heart cells beating in culture synchronize their rhythms through electrical and chemical signaling. Fireflies in Southeast Asian mangroves synchronize their flashing across hundreds of individuals. Could there be deep biological principles of synchrony and resonance that manifests in yawn contagion, among other phenomena? The narrative tying to cosmic themes works through the concept of resonance and synchronization across scales. Fish schools move as coordinated units, responding to each other's movements through lateral line sensors that detect water pressure changes. Flocks of birds turn simultaneously, each individual following simple rules about spacing and alignment that produce complex emergent patterns. At larger scales, planets orbit in resonances, gravitational interactions locking their periods into integer ratios. Jupiter's moons, Europa, Ganymede, and Io orbit in a 4-2-2-2-1 resonance, each orbital configuration repeating at cosmic scales. Galaxy clusters move under mutual gravitational influence, their dynamics coupled across millions of light years. Synchronization appears as a fundamental principle, organizing systems from molecular to cosmic scales. Oscillate is whether neurons firing, hearts beating, pendulums swinging, or planets orbiting tend to phase lock when coupled, their rhythms entraining to common frequencies. The mathematics of coupled oscillators reveals surprising commonalities across wildly different physical systems. Perhaps yawn contagion represents a biological instantiation of these universal synchronization principles, a social oscillator that couples through observation and triggers phasor-locked responses. September 20th, 2040 mark it on whatever calendar system survives the intervening years, because on that date the solar system will present a geometric arrangement rare enough to attract attention and common enough that similar configurations recur with predictable frequency. 6 planets: Mercury, Venus, Mars, Jupiter, Saturn, and Uranus will occupy a relatively narrow band of sky as seen from Earth. Their longitudes, the angular positions along the ecliptic, separated by less than 90 degrees. The media will undoubtedly call this a planetary alignment or parade, though technically the planets won't line up in a straight line. They'll simply cluster in one region of the sky, simultaneously visible from Earth's night side. The geometry works like this. Planets orbit the Sun in approximately the same plane, the ecliptic, defined by Earth's orbital plane. From our perspective, planets appear to move along a path across the sky that follows the zodiac constellations. Sometimes planets spread around. The entire ecliptic, visible at different times as Earth rotates. Other times, their orbital positions cluster so multiple planets appear in the same region of sky simultaneously. These clustering events occur regularly, but irregularly the result of planets, with different orbital periods occasionally lining up their positions. The rarity depends on how many planets we require to participate and how tightly we define alignment. Getting all 8 planets within a 90 band happens every few decades. Getting them within 30 happens every few centuries. Getting them in an actual straight line, all planets at 0 separation as seen from the Sun, probably never happens within human timescales, because orbital periods don't share exact integer ratios that would create perfect recurring alignments. The 2040 event will be particularly favorable for observation because the planetary cluster will include bright, naked-eye planets, Mercury, Venus, Mars, Jupiter, and Saturn, all easily visible without optical aid, plus Uranus, which requires binoculars or small telescopes. Neptune will be elsewhere in its orbit, not participating in the clustering. The planets will be visible in the evening sky after sunset, rising together in the east and arcing across the southern sky depending on observer latitude. Providing hours of viewing opportunity, amateur astronomers will have a field day, capturing all visible planets in one wide-angle photograph becomes possible during these events, creating images that showcase the architecture of the solar system. The different brightnesses and colors of planets provide visual interest. Venus appears brilliantly white, Mars distinctly orange-red, Jupiter yellowish white, Saturn similar to Jupiter but slightly fainter, Uranus barely visible as a pale blue-green disk even in binoculars. Photographing them together creates a portrait of planetary diversity compressed into a single frame. Professional astronomers will seize opportunities beyond pretty pictures. Planetary alignments don't create any special gravitational effects, despite persistent myths about tidal forces or seismic triggering, but they do provide occasions to make simultaneous measurements across multiple planets using the same instruments and techniques. Comparative planetology benefits from such opportunities, measuring atmospheric properties of Venus, Jupiter, and Saturn during the same observation window controls for instrumental and observational variables, allowing more confident comparisons. The alignment might also provide opportunities to detect unusual objects. When planets cluster, the background star field in that region gets observed more intensely than usual. Faint asteroids, distant comets, or even undiscovered planets in the outer solar system might be spotted by observers scanning the region looking for planets. The hypothetical Planet 9 proposed to explain orbital clustering of distant trans-Neptunian objects remains undiscovered despite searches. Its predicted location, if it exists, wanders slowly through the zodiac, and it might happen to be near the region of planetary clustering in 2040, making detection more likely simply because more telescopes will be pointed that way. Myth and cultural contexts surround planetary alignments across human history. Ancient astronomers tracked planetary positions carefully, noting conjunctions and alignments, attributing significance to these events. Astrological traditions, which persist despite lack of scientific support, assign meaning to planetary configurations based on symbolism and perceived correlations. The scientific worldview rejects these associations as pattern-seeking applied to random coincidence. But the human psychological response to celestial alignments remains strong. When planets gather in one part of the sky, it feels significant. Even if we intellectually understand it's just orbital geometry, some fringe communities will inevitably predict catastrophic consequences from the 2040 alignment. Planetary gravitational forces supposedly causing earthquakes or weather disasters represent recurring doomsday scenarios unsupported by physics. The gravitational influence of planets on Earth is negligible compared to the Moon and Sun. Even when planets align, their combined gravitational pull adds tiny perturbations to Earth's orbit that have no measurable effect on geological or atmospheric processes. But facts don't prevent predictions, and somewhere online someone will claim the alignment will trigger disasters and other people will believe them and prepare. And when the disasters don't materialize, the predictions will be quietly forgotten or rationalized away. Hidden scientific opportunities in alignments include mass distribution measurements in the solar system, precise tracking of planetary positions, allows tests of gravitational theories and refinement of planetary masses. Every planet affects every other planet, gravitationally creating perturbations in orbits that accumulate over time. By measuring where planets are and comparing to where Newtonian gravity predicts they should be, astronomers can detect anomalies that might indicate unknown masses elsewhere in the solar system or, more speculatively, deviations from gravitational theory itself. The cultural dimension of alignments as global events matters in an increasingly connected world. Unlike eclipses, which are visible only from specific geographic locations, planetary configurations are visible globally, weather permitting. This creates shared experiences across cultures and continents. In 2040, people in Tokyo and New York and Sydney and Lagos will see the same planetary arrangement, creating a moment of cosmic commonality that transcends political and cultural divisions. The comparison to a planetary choir works metaphorically. Each planet moves at its own tempo, Mercury racing around the Sun every 88 days. Neptune creeping along, taking 165 years per orbit. These different periods create complex rhythms and patterns over time. When planets cluster, it's like a moment in a long cosmic symphony where multiple instruments sound simultaneously, creating a chord before drifting apart again into individual melodies. The metaphor shouldn't be pushed too far because planets don't actually make sounds or create music, but it captures something true about patterns and rhythms in orbital dynamics. Foreshadowing the 2035 supermoon creates continuity in the narrative. These alignment events and close approaches mark time in ways that transcend individual human lifespans. Someone born in 2040 will be 12 years old when the supermoon occurs, will be 20 when Apophis makes its close pass, will be middle-aged before the next major planetary alignment. These cosmic events provide waypoints in generational memory, shared experiences that define eras and give structure to historical time beyond human constructs like decades and centuries. In 2060, something is going to happen that no living human has ever witnessed. The forecasts are already in, the orbital calculations already done, and astronomers are marking their calendars for an event that will rival anything in recorded history, a massive object from the Oort cloud, that distant reservoir of comets surrounding our solar system, is heading toward the inner solar system on a trajectory that will bring it close enough to the sun to become spectacular. Not just bright, not just visible, but potentially as luminous as the moon itself, dominating the night sky for weeks or possibly months. If the predictions hold, this comet will be the astronomical event of the century, a once-in-a-lifetime spectacle that will be visible even in daylight, casting shadows at night and fundamentally changing humanity's relationship with the sky, for everyone alive to see it. Let me put this in perspective. Most comets that pass through the inner solar system are faint, requiring binoculars or telescopes to see. A handful each decade become visible to the naked eye, appearing as fuzzy patches of light with modest tails. Every few decades we get a bright comet, something that makes headlines and draws people outside to look up. Comet Hale-Bopp in 1997 was one of these. Visible for over 18 months and bright enough to see easily from cities despite light pollution. Before that, Comet West in 1976 put on a spectacular show for those who woke up before dawn to see it. And of course, there's Halley's Comet, which returns every 75 to 76 years and has been documented by humans for over 2,000 years. Appearing in Babylonian records, Chinese chronicles, and the Bayer Tapestry. But even Halley's Comet at its best is just a bright comet. It's impressive, sure, but it doesn't dominate the sky. The 2060 comet, if it lives up to its billing, will do exactly that. Current models suggest it could reach an apparent magnitude of -10 or even -12, which would make it as bright as a half moon or possibly a full moon. To understand what this means, you need to know that the magnitude scale is logarithmic and backwards. The Sun has an apparent magnitude of -26.7. The full moon is 12.7. Venus at its brightest is about -4.9. A bright comet like Hale-Bopp topped out around magnitude -1. Each step represents roughly 2.5 times more light. So a magnitude -10 comet isn't just twice as bright as Hale-Bopp, it's thousands of times brighter. What creates a comet this spectacular? Size matters, obviously. The nucleus of the 2060 comet is estimated to be absolutely enormous, possibly 50 to 100 kilometers across, making it one of the largest objects ever to visit the inner solar system from the Oort cloud. For comparison, the nucleus of Comet Hale-Bopp was roughly 60 kilometers across, and that was already considered huge. But size alone isn't enough. The comet also needs to pass close to the sun, close enough that solar heating vaporizes massive amounts of ice, creating a coma that can grow larger than Jupiter and a tail that can stretch for hundreds of millions of kilometers. The 2060 comet checks all these boxes. Its perihelion will bring it within about 0.3 astronomical units, roughly 45 million kilometers, which is inside Mercury's orbit. At that distance, the sun's heat will vaporize not just water ice, but also more volatile compounds like carbon monoxide and carbon dioxide. But beyond the science, there's something deeper happening here. For one brief moment in 2060, humanity will share a common experience. People in every country, on every continent, will look up and see the same thing, a comet so bright it can't be ignored. So spectacular, it transcends language and culture and politics. The 2060 comet will be impossible to miss. It will dominate the twilight and nighttime sky, visible even from brightly lit cities, casting enough light to read by if you're in a dark location. And here's where things get interesting and maybe a little unsettling. What happens when you introduce a light source into the night sky that rivals the moon? We know that moonlight affects ecosystems. Nocturnal animals adjust their behavior based on lunar phases. Predators hunt differently during full moons. Human circadian rhythms, the internal clocks that regulate our sleep-wake cycles, are influenced by ambient light levels. For the entire time humans have existed, the moon has been the brightest object in the night sky. What happens when we throw a third variable into that equation? The truth is, we don't know. The comet will be visible for weeks, possibly months. And during that time, it will be pumping light into the nighttime environment at levels Earth hasn't experienced from a comet in recorded history. Now, let's talk about the less pleasant possibilities. Whenever a comet gets this close to Earth, people start worrying about impacts and catastrophes. Let me be clear, the 2060 comet is not going to hit Earth. Its orbit is well characterized, and it will miss us by millions of kilometers. But that doesn't mean it's completely harmless. Comets shed material as they approach the sun dust. Small particles, sometimes even larger fragments, break off and spread out along the comet's orbit. If Earth's orbit happens to intersect the comet's orbit after the comet has passed, we could encounter this debris stream, creating a spectacular meteor shower. But there's a more concerning scenario that, while unlikely, isn't impossible. Comets sometimes break apart as they approach the sun. The thermal stress, the tidal forces, the outgassing pressure, all of these can cause structural failure in a comet's nucleus. If the 2060 comet were to fragment, and if one of those fragments happened to have an orbit that brought it closer to Earth than predicted, we'd have a problem. The odds are extremely low, but it's not impossible. This is why asteroid and comet tracking has become such a serious endeavor. But hopefully, the dominant response will be awe, because whatever else it is, the 2060 comet will be beautiful. It will be a reminder that we live in a universe capable of creating spectacular phenomena. For a few weeks or months, dinner conversations will include discussions of tail structures and coma dynamics. Children will stay up late to see the comet. It will become part of the cultural fabric of that generation. And when it's over, when the comet has swung around the sun and is heading back to the outer solar system, we'll be left with photographs and memories. But even as it fades, there's another date on the cosmic calendar that represents an equally profound milestone. On February 18, 1930, a young astronomer named Clyde Tombaugh was examining photographic plates at the Lowell Observatory in Flagstaff, Arizona. He was searching for a predicted ninth planeter world beyond Neptune that might explain slight irregularities in the outer planet's orbits. The work was tedious, comparing pairs of photographs taken days apart, looking for anything that moved against the background of stars. And then he found it, a tiny dot that had shifted position between exposures. Planet X, the ninth planet, Pluto. The discovery made headlines around the world. Pluto was the first planet discovered by an American, and it captured the public imagination in ways that astronomical discoveries rarely do. The name Pluto, suggested by an 11-year-old girl, in England named Venetia Burney seemed perfect, the god of the underworld for the distant dark world at the edge of the solar system. For 76 years, school children learned that the solar system had 9 planets, and Pluto tiny and Mysterio was the last outpost before the great darkness of interstellar space. And then, in 2006, the International Astronomical Union redefined what it means to be a planet. Pluto met 2 of the 3 criteria, but failed the 3rd. It hadn't cleared its orbital neighborhood of other debris. Under the new definition, Pluto was reclassified as a dwarf planet, and the solar system was back to 8 planets. The demotion was met with surprising public outcry. People felt affection for Pluto, this distant underdog world. But here's something that puts all of this in perspective. In 2177, 247 years after its discovery, Pluto will complete exactly 1 orbit around the Sun. It will return to the same position in space where Clyde Tombaugh first spotted it on those photographic plates. Think about what that means. Pluto's year, the time it takes to complete 1 orbit's 247.9 Earth years. When Pluto was discovered in 1930, it had completed about 36% of 1 orbit since the Declaration of Independence was signed. We discovered Pluto, studied it, sent a spacecraft to fly by it in 2015, watched it get demoted and debated and argued over. And through all of this, Pluto hasn't even made it once around the Sun. This is a profound lesson in timescales. We humans live at best about 80 to 100 years. That's the span of direct memory and experience for any individual. Our civilizations last longer, with continuous written records going back about 5,000 years. But even on that scale, Pluto has completed only about 20 orbits. The entire span of human civilization covers just 20 trips around the Sun for this distant world. And if we zoom out further to the 4.5 billion year history of the solar system, Pluto has completed roughly 18 million orbits. That sounds like a lot, until you realize that Earth has completed 4.5 billion orbits in the same time. But it's not just Pluto. The outer solar system operates on timescales that dwarf human experience. Neptune takes 165 years to orbit the Sun. Since its discovery in 1846, Neptune has completed barely more than 1 orbit. Uranus takes 84 years. Saturn takes 29. These are worlds that move through the zodiac at a stately, almost imperceptible pace. Ancient astrologers only knew of 5 planets beyond Earth, because those are the only ones that move noticeably across the sky within a human lifetime. And this raises an interesting question. What's the longest time scale that humans can truly comprehend? We can intellectually understand that the universe is 13.8 billion years old, that the Sun formed 4.5 billion years ago. We can recite these numbers, put them in textbooks, teach them to students, but do we really grasp them? Can any human mind truly hold 13 billion years of time in its head in a way that feels real? Probably not. Our intuition is calibrated to human lifetimes, to the span of years we expect to live. Beyond a few generations, time becomes abstract. This is why Pluto's first birthday since discovery is such a poignant marker. It's a time scale that's just barely comprehensible to our civilization. 247 years spans from 1777 to 2177, over a century and a half in our future. It's longer than any human life, longer than most institutions survive, but short enough that we can trace cultural continuity. People in 2177 will be able to look back at records from Pluto's discovery and understand what those astronomers were doing and why it mattered. But when Pluto completes that first orbit in 2177, it will just be beginning its second orbit since discovery. And that second orbit will take another 247 years. Pluto won't complete a third orbit until 2671. The people who will witness Pluto's second birthday haven't been born yet and won't be born for centuries. And by then, will humans still care about Pluto? Will we still be watching the skies, tracking the planets, marking these cosmic milestones? I'd like to think we will be, despite everything. Despite the chaos that often characterizes human behavior, we've maintained astronomical observatories for centuries. We've kept records passed down, knowledge built on the discoveries of previous generations. The fact that we can calculate Pluto's orbit and predict its position in 2177 is a testament to the power of accumulated knowledge, of humans working across generations toward common goals. And speaking of long time scales, consider this. When 3I Atlas entered our solar system in 2024, it had been journeying through interstellar space for millions of years. If it was ejected from a star system 10 light years away, traveling at 66 kilometers per second, it would have taken about 45,000 years to cover that distance. During that entire time, this comet was frozen, unchanged, drifting through the void, and then it spent a few months in our solar system, got destroyed by the sun, and was gone. But understanding isn't the same as experiencing. We can calculate Pluto's orbit, but we can't feel what it's like to take 247 years to circle the sun. We can measure the sun's lifetime at 10 billion years, but we can't viscerally grasp that span of time. We're bounded by our biology, our mortality, our place in space and time. When Clyde Tombaugh discovered Pluto in 1930, he was 24 years old. He died in 1997 at age 90, having lived to see spacecraft visit every planet in the solar system, to see humans walk on the moon. But he never saw Pluto complete an orbit. No human who was alive when Pluto was discovered will live to see its first birthday. That milestone will belong to people not yet born. Let's shift gears and talk about something that connects all these cosmic events. Something that underlies our ability to predict planetary alignments, track asteroids, and understand the dance of celestial bodies across the sky. I'm talking about gravitational physics, the invisible force that governs the motion of everything from moons to galaxies. And here's the thing, while we've mastered Newton's laws and Einstein's relativity to the point where we can land rovers on Mars with pinpoint accuracy, there are still profound mysteries lurking in the gravitational realm. In 2023, physicists announced the most precise measurement yet of the gravitational constant, a fundamental number that appears in Newton's law of universal gravitation. This constant determines the strength of gravitational attraction between masses, despite being one of the first physical constants ever measured. G remains the least precisely known of all the fundamental constants. The new measurement, using a sophisticated torsion balance apparatus in a subterranean laboratory, reduced the uncertainty to just 0.001 0.0012%. That sounds impressive, but here's the puzzle. Different experimental methods keep producing values of G that don't quite agree with each other, even when accounting for stated uncertainties. The discrepancy is small, just a few parts per 100,000, but it's persistent, and it has physicists scratching their heads. What could explain this discrepancy? Some researchers suspect systematic errors that haven't been identified in the experiments. Others wonder if there might be new physics at play. Perhaps gravity behaves slightly differently under certain conditions than our theories predict. One intriguing possibility involves extra dimensions of space. String theory and related approaches to quantum gravity suggests there might be additional spatial dimensions beyond the three we experience, curled up so small we don't notice them. If these dimensions exist, gravity might leak into them, explaining why it appears so weak compared to the other fundamental forces under certain experimental conditions. This leakage might vary, producing the observed discrepancies in G measurements. Another gravitational mystery comes from observations of galaxies rotating too fast for their visible matter to explain. The discrepancy led astronomers to propose dark matter mass that provides additional gravitational pull. But what if the problem isn't missing matter, but rather incorrect gravity? Modified Newtonian dynamics, Mont proposes that gravity behaves differently at extremely low accelerations, such as those found in the outer regions of galaxies. Mont can explain galaxy rotation curves without invoking dark matter, but it struggles with other observations like the Bullet cluster, where two galaxy clusters collided and separated dark matter from visible gas in ways that seem to require dark matter to explain. The debate continues, with new observations from the James Webb Space Telescope and other facilities, providing fresh data to test both approaches. The connection to our cosmic events becomes clear when you consider how gravitational mysteries affect our ability to predict future celestial mechanics. The 2029 Apophis flyby, the 2040 planetary alignment, the 2060 comet. These predictions rely on our understanding of gravity. If there are subtle errors in our gravitational models, they could accumulate over decades or centuries, potentially shifting predicted positions enough to matter for close approaches. For most objects, the uncertainties remain small enough not to matter. But for objects passing very close to Earth, even tiny errors could be significant. This is why astronomers continue to refine orbital calculations as new observations become available. Each new measurement of an asteroid's position helps constrain its orbit, reducing uncertainty about future encounters. The gravitational constant might be mysterious, but the practical effects of its uncertainties are minimized through continuous observation and adjustment. Still, the fundamental questions remain. Why is gravity so much weaker than the other forces? Why does dark matter, if it exists, interact only gravitationally with normal matter? Are there extra dimensions affecting gravitational behavior? These aren't just abstract puzzles. They have real implications for how we understand the cosmos and our place within it. The gravitational constant measurement connects to another cosmic mystery, the fine-tuning problem, the fundamental constants of nature, the strength of gravity, the charge of an electron, the mass of a proton appear to have values that allow for the existence of complex structures like stars, planets, and life. If these values were even slightly different, the universe would look radically different, potentially unable to support life. Why do these constants have the values they do? One possibility is that there are many universes, each with different constants, and we find ourselves in one that can support us because we couldn't exist in the others. This anthropic principle satisfies some, but feels like a cop-out to others. Another possibility is that there's some deeper theory that determines these values uniquely. We just haven't discovered it yet. The gravitational constant also connects to quantum mechanics through the problem of quantum gravity. We have two spectacularly successful theories of the physical world: general relativity for gravity and the quantum field theory for the other forces and particles. But these theories are incompatible at the most fundamental level. Relativity describes gravity as the curvature of space-time, while quantum mechanics describes everything else in terms of discrete particles and fields. Unifying these approaches into a theory of quantum gravity remains perhaps the single greatest challenge in theoretical physics. String theory, loop, quantum gravity, and other approaches offer potential paths forward, but none has produced testable predictions yet. The connection to our cosmic narrative becomes personal when you consider that every atom in your body was forged in stars that lived and died billions of years ago. The elements heavier than hydrogen and helium were created through nuclear fusion in stellar interiors or during supernova explosions. These processes depend critically on the strengths of the fundamental forces, including gravity. If gravity were slightly stronger, stars would burn hotter and die faster, potentially leaving insufficient time for life to evolve on any planets that formed. If gravity were slightly weaker, stars might not ignite at all, leaving a universe of hydrogen and helium gas with no heavy elements to make planets or people. We exist, in other words, because gravity has the strength. It does a thought that adds cosmic significance to every measurement of G, no matter how precise or uncertain. The gravitational mysteries also connect to the search for extraterrestrial intelligence. If the fundamental constants were different in other parts of the universe, it could affect the development of life elsewhere. Some physicists have speculated that there might be islands in the multiverse where the constants take values particularly conducive to the emergence of complex life and intelligence. If such islands exist, they might be the places most likely to harbor technological civilizations. This is highly speculative, of course, but it illustrates how fundamental physics connects to the biggest questions. We can ask about our place in the cosmos as we continue to watch the skies for 3I Atlas, track Apophis, and anticipate the 2060 comet. We're participating in a grand human tradition that stretches back thousands of years. We're looking for patterns, trying to understand the rules that govern the cosmos, and seeking our place within the cosmic order. The gravitational mysteries remind us that despite all we've learned, there are still deep questions to answer about how the universe works. Each new measurement, each observation, brings us closer to understanding these mysteries, while sometimes revealing new layers of complexity beneath what we thought we knew. Let's talk about something that connects all these cosmic events in a way you might not expect: time. Not just the passage of time, but how we measure it, how we perceive it, and how it shapes our understanding of the universe. In 2024, international timekeeping agencies announced a controversial decision to abolish the leap second by 2035. This might sound like a technicality only horologists would care about, but it has profound implications for everything from GPS navigation to our fundamental relationship with cosmic time. First, some background. The leap second was introduced in 1972 to address a growing discrepancy between two ways of measuring time. Universal time, UT1, is based on Earth's rotation relative to the Sun's, the traditional solar time that gives us days and nights. Coordinated Universal Time, UTC, is based on atomic clocks, which measure time by the oscillations of atoms, precise and stable. The problem is that Earth's rotation is gradually slowing down due to tidal friction from the Moon. This means UT1 and UTC gradually drift apart, with the atomic day becoming slightly shorter than the solar day. To keep them aligned, timekeepers occasionally add a leap second to UTC, essentially pausing atomic time for a moment to let Earth's rotation catch up. Since 1972, 27 leap seconds have been added, with the most recent occurring on December 30, 2016. But here's the controversy. Leap seconds create headaches for computer systems and navigation technologies. GPS, for example, doesn't use leap seconds. It maintains its own timescale that has diverged from UTC by 18 seconds since 1980. When a leap second is added, computer systems can crash or malfunction if they're not properly programmed to handle it. The 2012 leap second caused outages at Reddit, Mozilla, and other sites. The 2015 leap second disrupted systems on the New York Stock Exchange. These problems have led many technologists to argue for abolishing the leap second altogether. The decision to phase out leap seconds by 2035 means that UTC will gradually drift away from solar time. Within a few centuries, noon by the clock will occur significantly before or after the sun reaches its highest point in the sky. For most daily purposes, this won't matter much. Our lives are already decoupled from solar time by time zones and daylight saving time, but for astronomical observations, navigation, and any application that requires precise alignment with Earth's orientation in space, the divergence will create complications that will need to be managed through other means. The leap second controversy highlights a deeper tension between two different ways of thinking about time. One view sees time as something natural, tied to Earth's rotation and the cycles of the sun and moon. The other sees time as something abstract and regular, best measured by the precise oscillations of atoms. This tension reflects our broader relationship with the cosmos. We want to understand natural cycles while also imposing regular, predictable structures on them. The connection to our cosmic events becomes clear when you consider how we predict and observe them. The timing of the 2029 Apophis, flyby, the 2040 planetary alignment, the 2060 comet, these predictions rely on precise timekeeping. If our time standards drift from Earth's actual rotation, it could affect observations, especially for objects that pass very close to Earth. The consequences on catastrophic. Astronomers can and do make corrections for these discrepancies, but they illustrate how even the most technical aspects of timekeeping connect to our cosmic understanding. Time perception adds another layer to this story. Humans experience time subjectively. Time flies when we're having fun, crawls when we're bored or anxious. This subjective experience of time has no connection to the precise measurements of atomic clocks or the gradual slowing of Earth's rotation. Yet it shapes how we relate to cosmic events that unfold on timescales far beyond human experience. When we talk about Pluto taking 247 years to orbit the Sun, or the 2060 comet returning after millions of years, we're trying to compress timescales that exceed our comprehension into frameworks we can understand. The psychological dimension of time perception connects to how we respond to cosmic threats and opportunities. The 2029 Apophis flyby feels urgent because it will happen within many of our lifetimes. The 2060 comet feels more distant because it's beyond our immediate planning horizon. Climate change presents a similar challenge. The most severe consequences will unfold over decades to centuries, making it difficult for our brains evolve to respond to immediate threats, to prioritize action. Understanding how we perceive time and how that perception differs from physical reality might help us make better decisions about long-term challenges. The measurement of time also connects to fundamental physics. The most precise atomic clocks are so sensitive they can detect tiny differences in gravitational fields due to general relativity. Clocks at higher elevations run slightly faster than clocks at lower elevations because they're in weaker gravitational fields. This effect, called gravitational time dilation, has practical applications. GPS satellites must account for it to maintain accuracy. But it also illustrates how time and gravity are intimately connected in ways that challenge our everyday understanding of time as uniform and absolute. The philosophical dimension of time measurement raises profound questions. Is time something fundamental to the universe, or does it emerge from more basic processes? Some physicists argue that time might be an illusion, a product of how our brains process information. Others suggest that at the quantum level, time might not exist in the way we experience it. These debates connect to our cosmic narrative because they affect how we think about the history and future of the universe. Did time have a beginning with the Big Bang? Will it have an end? These questions remain unanswered, but each advance in time measurement and theoretical understanding brings us closer to resolving them. The leap-second decision also reflects how human systems evolve in response to technological change. For most of human history, timekeeping was tied to natural cycles, sundials, water clocks, mechanical clocks regulated by Earth's rotation. The development of atomic clocks in the mid-20th century created a new paradigm for time measurement. More precise than anything that came before, the leap second was an attempt to bridge these two paradigms. But as technology becomes increasingly dependent on precise, regular timekeeping, the bridge is being abandoned in favor of technical convenience. This pattern repeats throughout human history. New technologies enable new capabilities, while creating new challenges that require new solutions. As we continue to track cosmic events across time scales from seconds to billions of years, we're participating in a grand human project of understanding time in all its aspects. From the subjective experience of watching a comet cross the sky to the precise measurements that allow us to predict planetary alignments centuries in advance. Time connects us to the cosmos in ways that are both practical and profound. The abolition of the leap second might seem like a small technical change, but it represents another step in our evolving relationship with time, a relationship that continues to shape how we understand our place in the universe. Let's zoom out from individual cosmic events and consider the bigger picture, how all these phenomena fit into our evolving understanding of the universe itself. In 2024, cosmologists announced new evidence from the James Webb Space Telescope that challenges our standard model of cosmology, suggesting the universe might be expanding slightly faster in some directions than others. This apparent directional variation in the expansion rate, if confirmed, would force a major revision of how we understand cosmic evolution and our place within it. The standard cosmological model, called lambda CDM, describes a universe that began with the Big Bang 13.8 billion years ago, initially expanded rapidly, then slowed its expansion due to gravity, and about 5 billion years ago began accelerating, again due to dark energy, a mysterious force that counteracts gravity on cosmic scales. This model has successfully explained a wide range of observations, from the cosmic microwave background radiation to the distribution of galaxies. But it's always had puzzles, including the nature of dark matter and dark energy, which together make up about 95% of the universe's energy density but remain fundamentally mysterious. The new Webb observations add another layer of complexity. By measuring the redshifts and distances to distant galaxies with unprecedented precision, astronomers found subtle variations in the Hubble. Constant the rate of cosmic expansion, depending on which direction they looked. In some parts of the sky, the expansion appears slightly faster than in others. The differences are small, just a few percent, but they're systematic and persist across multiple independent measurements. If this anisotropic expansion is real, it would mean the universe isn't perfectly uniform and isotropic on large scales, contrary to a fundamental assumption called the cosmological principle that underlies most cosmological models. Several explanations have been proposed for these observations. One possibility is that we're seeing the effects of a vast cosmic structure, a supercluster of galaxies pulling on matter in its vicinity, creating the appearance of faster expansion in that direction. Another possibility involves exotic physics, perhaps. Dark energy itself varies across space, or there are additional dimensions affecting how gravity works on cosmic scales. A more mundane explanation would be systematic errors in the observations or their analysis. Though the Webb team has been careful to account for known sources of error, the connection to our cosmic narrative becomes clear when you consider how these large-scale cosmic structures affect the motion of objects within our galaxy. The gravitational influence of distant galaxy clusters and superclusters can subtly affect the orbits of comets in the Oort cloud, potentially sending them toward the inner solar system. The 2060 comet's journey toward the Sun might have been triggered millions of years ago by the gravitational influence of a passing galaxy or a massive cosmic structure. Similarly, the trajectories of near-Earth asteroids like Apophis are shaped not just by the planets, but by the gravitational landscape of the entire universe. The anisotropic expansion findings also connect to the cosmic microwave background, faint radiation left over from the Big Bang that provides a snapshot of the universe when it was just 380,000 years old. This radiation shows tiny temperature fluctuations that seeded the formation of galaxies, and galaxy clusters. If the universe's expansion varies by direction, it might leave imprints in the cosmic microwave background that future observations could detect. The Planck satellite and other instruments have already mapped this background radiation in exquisite detail. But new analysis techniques might reveal subtle patterns that previous studies missed the philosophical implications of these findings. Are profound. For centuries, we've understood the universe as fundamentally uniform, the same everywhere and in every direction. This assumption of isotropy has been central to cosmological thinking since the early 20th century. Finding that the universe might be slightly lopsided would force us to reconsider our place in the cosmos. Are we in a typical region of the universe, or do we happen to be in an unusual area? The answer affects how we interpret cosmological observations and how we think about the conditions that allowed life to evolve on Earth. The anisotropic expansion also connects to the search for extraterrestrial intelligence. If the universe varies significantly from place to place, it might affect the development of life elsewhere. Regions with slightly different expansion rates might have different histories of structure formation, potentially affecting the distribution of galaxies, stars, and planets. This could influence where and when life might arise in the universe. Consideration that adds another layer to the Drake equation and other frameworks for estimating the prevalence of extraterrestrial civilizations. The Webb observations illustrate how technological advances drive scientific progress. Each new generation of telescopes reveals new aspects of the universe, challenging our theories and expanding our understanding. The James Webb Space Telescope, with its infrared capabilities and unprecedented sensitivity, is particularly well suited to studying the early universe and distant galaxies. Its observations of anisotropic expansion represent just one example of how this remarkable instrument is pushing the boundaries of cosmology. The connection to our time measurement discussion from the previous section becomes apparent when you consider how cosmic expansion affects our understanding of time itself. In an expanding universe, there's no absolute time. Time passes differently depending on your motion and gravitational environment. The apparent directional variation in expansion rates adds another layer of complexity to how we think about cosmic time and our place within it. When we talk about events happening billions of years ago or billions of years in the future, we're implicitly assuming a uniform cosmic clock that might not exist if the expansion varies by direction. The anisotropic expansion findings also connect to dark energy, the mysterious force driving the accelerated expansion of the universe. If dark energy varies across space, it might help explain why its observed value is so small compared to theoretical predictions. This cosmological constant problem is one of the biggest puzzles in fundamental physics. Quantum field theory predicts a value for dark energy that's about 120 orders of magnitude larger than what we observe. Finding that dark energy varies by direction wouldn't solve this discrepancy, but it might provide clues about its fundamental nature as we continue to observe cosmic events like the 2040 planetary alignment and the 2060 comet. We're gathering data that helps constrain cosmological models. Each precise measurement of planetary positions, each observation of distant comets contributes to our understanding of the gravitational dynamics that shape the universe. The apparent anisotropic expansion reminds us that even our most fundamental Assumptions about the cosmos should be continually tested against observations. The universe has surprised us before, and it will likely surprise us again as our observational capabilities continue to improve. The philosophical dimension of these findings touches on how we understand our relationship to the cosmos. If the universe is not perfectly uniform, if it has structure and variation on the larger scales, it becomes more like the complex, varied world we experience on Earth. This doesn't diminish the wonder of the cosmos. If anything, it makes it more interesting and perhaps more hospitable to the kind of complexity that leads to life. As we continue to explore these questions, we're not just learning about the universe, we're learning about ourselves and our place within the grand cosmic scheme. Let's bring our cosmic journey full circle and return to where we began with the mysterious disappearance of Comet 3I Atlas behind the Sun during a massive solar storm. As astronomers continue to watch for its emergence, the story has evolved. From a simple astronomical event into a case study in how science works, how information spreads in the digital age, and how we collectively make sense of phenomena that challenge our understanding. In the weeks following 3I Atlas's disappearance, a fascinating pattern emerged in how different communities responded to the event. Professional astronomers maintained cautious optimism, emphasizing that comets often behave unpredictably, and that disappearance behind the Sun doesn't necessarily mean destruction. They pointed to historical examples like Comet Lovejoy, which survived a perilously closed solar passage in 2011 despite predictions of disintegration. They highlighted the many uncertainties in comet models and the need for patience until observational conditions improved. Amateur astronomers took a more hands-on approach, organizing coordinated observation campaigns to be ready when the comet emerged from solar conjunction. Online forums buzzed with technical discussions about optimal viewing equipment, observation schedules, and image processing techniques. This grassroots effort represented citizen science at its best, enthusiastic observers, contributing to a collective scientific endeavor without formal institutional support. Science communicators worked to translate the technical details into accessible narratives, explaining the significance of an interstellar comet and the challenges of observing objects near the Sun. They balanced excitement about the scientific opportunity with caution against premature speculation, walking a fine line between engaging public interest and avoiding sensationalism. But in other corners of the internet, very different narratives took shape. Conspiracy theorists found fertile ground in the timing of the comet's disappearance with a solar storm and earthquakes. Some claimed the comet had been deliberately destroyed to prevent it from revealing information about advanced extraterrestrial civilizations. Others suggested the solar storm wasn't natural, but rather a weapon aimed at the comet. These narratives spread rapidly through social media algorithms that prioritize engagement over accuracy, creating parallel information ecosystems where the same events were interpreted in radically different ways. The response to 3I Atlas illustrates a broader challenge in modern science communication. In an era of information abundance, expertise no longer guarantees authority. A professional astronomer with decades of experience and access to the best data might have less influence on public opinion than a charismatic content creator with millions of followers and a compelling narrative. This democratization of information has positive aspects. More voices can contribute to scientific discourse, but it also creates challenges when expertise is devalued and misinformation spreads as easily as verified information. The psychological dimension of this phenomenon connects to how our brains process information. We're wired to respond to stories that create emotional engagement, that provide clear explanations for complex phenomena, and that confirm our existing beliefs. Scientific explanations are often nuanced, probabilistic, and subject to revision that make them less compelling than definitive narratives that offer simple answers to complex questions. The conspiracy theories about Three-Eye Atlas provided clear villains, government agencies hiding the truth, clear heroes, independent researchers uncovering secrets, and a clear moral dimension, the struggle between truth and deception elements that make for engaging storytelling, even if they have no basis in reality. The economic dimension shouldn't be overlooked either. In the attention economy, dramatic claims generate more clicks, shares, and revenue than cautious scientific explanations. Content creators who framed the Three-Eye Atlas disappearance as a mystery with hidden meanings often outperformed those who stuck to the scientific consensus. This creates perverse incentives that reward sensationalism over accuracy, contributing to the fragmentation of shared understanding about reality. The technological dimension connects to how our information environment has evolved. Traditional media operated with editorial standards and fact-checking processes that provided some quality control. Social media platforms distribute content without these gatekeeping functions, allowing misinformation to spread rapidly. Algorithmic recommendation systems, designed to maximize engagement, often promote content that elicits strong emotional responses, regardless of its accuracy. These technological factors have fundamentally changed how information spreads and how public opinion forms. The educational dimension highlights gaps in science literacy that make people vulnerable to misinformation. Understanding why comets sometimes disappear behind the sun, how solar storms affect Earth, and how scientists assess probabilities requires some background knowledge that many people lack. Without this foundation, dramatic claims can seem just as plausible as scientific explanations. Improving science education could help build resilience against misinformation. But this is a long-term solution to an immediate problem. The political dimension connects to broader trends of distrust in institutions. In many countries, confidence in government, media, and scientific institutions has declined over recent decades. This erosion of trust creates fertile ground for alternative narratives that position institutional authorities as untrustworthy. The conspiracy theories about Three-Eye Atlas often cast government agencies and mainstream scientists as part of a cover-up. Tapping into this broader pattern of institutional distrust, the ethical dimension raises questions about responsibility. Scientists have a responsibility to communicate clearly and accurately, but do they also have a responsibility to actively counter misinformation? Journalists have a responsibility to report truthfully, but do they have a responsibility to avoid amplifying false narratives even when they generate audience engagement? Platform designers have a responsibility to create systems that connect people with information. But do they have a responsibility to prevent the spread of harmful misinformation? These questions don't have easy answers, but they're increasingly important as our information environment evolves. The philosophical dimension touches on how we determine what's true. In a world of abundant information and limited expertise, how do we distinguish between reliable and unreliable sources? How do we balance openness to new ideas with healthy skepticism? How do we maintain a shared reality when different groups accept fundamentally different versions of events? These epistemological questions have become pressing practical concerns in our digital age. As we await the emergence of 3i Atlas from behind the sun, whatever the outcome, the event has already provided valuable insights into how modern society processes scientific information. The comet itself might be destroyed or intact, but the information ecosystem surrounding it has already been transformed by the experience. Whatever we learn about the comet, we've learned even more about ourselves, how we seek meaning, how we form beliefs, and how we navigate the complex information landscape of the 21st century. The response to 3i Atlas illustrates both the strengths and weaknesses of our current approach to understanding the cosmos. We have remarkable technological capabilities that allow us to detect interstellar visitors and observe them across vast distances. We have sophisticated theoretical frameworks that help us interpret these observations. But we also have information systems that sometimes undermine rather than support our collective understanding. Moving forward, improving how we process and share scientific information might be just as important as improving our telescopes and other observational tools. As we reach the conclusion of our cosmic journey, let's step back and consider the bigger picture that emerges from all these diverse phenomena. From disappearing comets and quantum communication to gravitational mysteries and the challenges of modern science communication, what connects these seemingly disparate events is a fundamental human drive to understand our place in the universe, to make sense of the cosmos and our relationship to it. The story of 3i Atlas, whether it emerges intact or has been destroyed by the sun, represents more than just an astronomical event. It embodies the scientific process, its self-observation, hypothesis, prediction, and testing. It illustrates how science progresses not through sudden breakthroughs, but through the gradual accumulation of evidence, the refinement of theories, and the willingness to revise our understanding in light of new observations. The comet also reminds us that nature often surprises us, that the universe contains phenomena that challenged our existing knowledge and push us to develop better explanations. The quantum communication network in China highlights how our understanding of fundamental physics translates into technological capabilities that reshape society. The ability to create unhackable communication channels exploits some of the strangest aspects of quantum mechanics: entanglement, the uncertainty principle, the observer effect. These technologies don't just represent practical applications. They're manifestations of deep physical principles that govern reality at its most fundamental level. As quantum technologies continue to develop, they'll increasingly transform how we communicate, compute, and interact with the world. The yeast that converts urine into bone mineral demonstrates how synthetic biology is blurring the boundaries between natural and artificial systems. By reprogramming cellular metabolism, scientists are creating biological machines that perform useful functions, producing materials, generating energy, detecting disease. This technology raises profound questions about the relationship between biology and engineering, about what counts as natural versus artificial, and about how we might redesign living systems to address human needs. The medical applications alone could revolutionize how we treat injuries and degenerative conditions. The discovery of contagious yawning in zebrafish challenges our assumptions about animal cognition and the evolution of social behaviors. If fish can exhibit contagious yawning without the neural structures we thought necessary for this behavior, what does this tell us about how social behaviors evolve? It reminds us that consciousness and cognition aren't uniquely human traits, but exist on a spectrum across the animal kingdom. Each discovery that blurs the boundaries between human and animal cognition forces us to reconsider our ethical relationship to other species. The 2029 Apophis flyby and the 2040 planetary alignment represent predictable cosmic events that connect us to the clockwork of the solar system. These alignments provide opportunities for scientific observation, public engagement with astronomy, and reflection on our place in the cosmos. They also remind us that Earth exists within a dynamic cosmic environment, that our planet is part of a larger system that operates according to physical laws we can understand and predict. The 2035 supermoon and the 2060 comet represent more extreme cosmic phenomena that will dominate Earth's skies. These events remind us that the cosmos is not static but dynamic, that spectacular phenomena can appear without warning and transform our relationship to the night sky. The 2060 comet, in particular, could become a generational touchstone shared experience that connects people across cultures and continents to the wonder of the universe. Pluto's first completed orbit, since its discovery in 2177, represents a different kind of cosmic event, one that operates on timescales far beyond human experience. This milestone reminds us that the universe operates according to schedules that ignore human concerns, that celestial bodies follow their paths through space over periods that dwarf human civilizations. Thinking about such timescales helps put human concerns in perspective, reminding us that we're temporary participants in a cosmic drama that began long before we appeared, and will continue long after we're gone. The measurement of the gravitational constant and the discovery of anisotropic cosmic expansion remind us that even our most fundamental theories of the universe are provisional, subject to revision in light of new evidence. These findings illustrate how science progresses by identifying discrepancies between prediction and observation, then developing new theories to explain them. They also highlight how much we still don't know about fundamental aspects of reality, from the nature of gravity to the large-scale structure of the universe. The decision to abolish leap seconds by 2035 represents a small technical change with profound implications for how we relate to cosmic time. This decision reflects the tension between natural cycles tied to Earth's rotation and the precise regularity of atomic timekeeping. It also illustrates how human systems evolve in response to technological change, often prioritizing technical convenience over traditional connections to natural cycles. The response to 3I Atlas's disappearance illustrates the challenges of science communication in the digital age. The fragmentation of shared understanding about reality, the spread of misinformation, and the erosion of trust in institutions all pose challenges to our collective ability to make sense of scientific developments. Addressing these challenges will require improvements in science education, more responsible information systems, and renewed efforts to build public trust in scientific institutions. What emerges from this survey of cosmic phenomena is a picture of humanity at a pivotal moment in our relationship to the universe. We have developed remarkable technological capabilities that allow us to observe the cosmos in unprecedented detail, to manipulate matter at the quantum level, and to redesign biological systems. We have constructed sophisticated theoretical frameworks that explain phenomena from subatomic particles to the large-scale structure of the universe. Yet we still face fundamental mysteries about the nature of reality, the origins of the universe, and our place within it. Perhaps most importantly, we face the challenge of translating our scientific understanding into collective wisdom that can guide our decisions as a species. The same technologies that enhance our understanding of the cosmos also create new risks and ethical dilemmas. Quantum communication could create more secure systems, but also enable new forms of surveillance. Synthetic biology could solve medical problems, but also create dangerous organisms. Space exploration could inspire humanity, but also become another arena for geopolitical competition. As we continue to explore the cosmos and develop new technologies, we need to cultivate not just scientific knowledge, but also wisdom, the ability to use knowledge responsibly, to consider long-term consequences, to balance individual and collective interests, and to maintain our connection to the natural world even as we transform it. The cosmic perspective, with its vast timescales and distances, can help cultivate this wisdom by reminding us of our small but precious place in the universe. The events we've discussed, from comets and planets to quantum technologies and gravitational mysteries, represent different facets of humanity's ongoing relationship with the cosmos. They illustrate our curiosity, our creativity, our capacity for understanding, and our limitations. They remind us that we're part of something much larger than ourselves, that we're temporary participants in a cosmic story that began billions of years before we appeared, and will continue billions of years after we're gone. As we look to the future, whether toward the emergence of 3I Atlas from behind the sun, the 2029 Apophis flyby, the 2040 planetary alignment, the 2035 supermoon, the 2060 comet, or even Pluto's completed orbit in 2177, we can approach these cosmic events with a sense of wonder, humility, and responsibility. Wonder at the beauty and complexity of the universe. Humility about how much we still have to learn, and responsibility for how we use our growing knowledge and capabilities. The cosmos continues to surprise us, to challenge our understanding, and to inspire us to ask new questions. Each observation, each experiment, each theoretical advance adds another piece to the grand puzzle of reality. As we continue this cosmic quest, we're not just learning about the universe, we're learning about ourselves, our potential, and our place within the grand cosmic scheme. And that might be the most profound discovery of all.